Yeah, and this area.
This fellow is making a lot of sound there. Kind of noise it is making.
Okay, so I'm sitting here.
అంటే ఇప్పుడు ఈ మైక్రోఫోన్ కల్లే లాగుతుంది ఆ సౌండ్ మైక్రోఫోన్ ఇది మైక్రోఫోన్ ఓకే బట్ కన్వీనియంట్ ఇప్పుడు అక్కడ ఏదైనా మార్చుకోవాలంటే అంత దూరం పోవాలి కొన్ని వీడియోస్ ఉంటాయి అట్లా క్లిక్ చేయాల్సి వస్తుంది 100% దాంతో ఆపరేట్ చేయడు మీరు 10% కంటెంట్ అది అంత కన్వీనియంట్గా ఉండలేము మేబీ ఇక్కడి
This
నుంచి ఆపరేట్ చేస్తే కన్వీనియంట్గా ఉండలేము
this way. Oh.
No, they are suggesting like if this microphone, that fellow is making sound. If you switch off also, that is making noise.
It's okay.
Are you able to manage like from here like this? Maybe.
Yeah, okay.
Uh,
Sure. I try.
Sorry for that.
No problem. Yeah.
This is making a lot of noise. And
Yeah,
that is
but only
capturing
this
that.
one. This one is quite quiet.
Yeah. ఇది ఆన్ చేసిందా బాబు ఇది ఆన్ చేసిందా ఆయన చేసిందంటే మీకు తెలియదు రెడ్ కనిపిస్తుంది
Okay. Sure, sure. You mean standing here?
Yes,
Yeah, yes,
yes,
it's okay. Yes.
why because that your microphone so if you are standing there that noise is capturing and in the live it is
Okay,
in the
okay,
YouTube
sure,
live
sure,
that
sure.
noise is ఇది ఓకేనా ఇట్లుంటేనా
Think probably yes, probably it's time to start. So shall I start or
wait
okay?
because they are going to switch off the entire AC in the hall that's what they are teaching that is the solution అంటే ఆయన మాట్లాడినాక మీ వినే ఉంది కదా నన్ను అడుగుతారు పని చేసిన సౌండ్ వస్తుంది కదా పని చేసిండా బట్ మరి ఏం ఇక్కడ ఏమన్నా ఉందా నాయిస్ బయట బయట ఓకే ఇక్కడ ఏసీ వేసినా వేయకపోయినా అలాగే ఉంది కదా ఏసీ ఏంటి
Yeah, shall we start?
Yeah.
So this
ఏసీ
good morning everyone. This lecture is actually dedicated to the fundamental of data-driven and its application in additive manufacturing, basically simulation as well. So just want to start this lecture with these two. One is actually trying to predict not exactly the same, but trying to do something for 3D printing. One is quite high fidelity modeling, another one is more simplified. So we'll talk today about how can we actually choose or how can we make this rapid calculation for data-driven simulation, for example. So in order to start the presentation, I just want to begin with what I think we don't know much each other. So I just begin with what I'm interested in terms of research. So my research lie into, so you may know, I give a lot of things on the computational material science and engineering. And then using multi-scale multi-physics modeling, this is one of the things that you saw in the past 2 days is actually related to, I mean, mostly is my research area. And then especially looking at the thermofluid dynamics of liquid metal that can apply not only to additive, but also for casting, welding, and all laser melted or molten pool dynamics here. And this is the thing that I think I'm also interested in this one, which is about the topic of today's talk. It is a digital material design. So you will see that we need to use artificial intelligence and data-driven modeling to understand what is happening in the metallurgical process. And then I want to actually working with experimentalists, especially the institute kind of experiment through synchrotron or neutron diffraction or imaging to understand the behavior of the material during the process. So it's quite fundamental understanding, not really going to the end user. But what we try to do is a fundamental for additive manufacturing that allow us to establish something more scientific-based model. So I hope I also highlight some example that we have done. So this is actually related to the model and the X-ray synchrotron published, I think, early this year in Nature.com, for example, and also understand the phenomenon happening in additive manufacturing. So physics-based model is basically something that we know is more preferable for scientific community, but probably we need to find a way to actually validate it for sure, whatever how difficult it is, but with the most delicate or more advanced technique that we can use to look at what happened. At the same time, we also want to build this knowledge in order to build a science-based data-driven platform that can enable us to get some data-driven model that established toward the material informatics for additive manufacturing. So the key words here is quite important. From the material informatics is something I will give example on last day, the final day of this short course here. And then another thing that probably benefit from for someone will say about digital twin is actually we call real-time prediction for the model that we are going to give a bit information today as well in this lecture. So next one is more complicated thing, is to look to probably to me and probably to you that is not really additive anymore, but it's actually relevant in terms of fundamental understanding of chemical thermal fluid dynamics during the non-equilibrium microstructure process. And this is also give us insight into the extra information that I probably dedicated one single lecture for this probably tomorrow as well. And this is something I just want to share with you. This is a digital twin that we probably very first one to publish for metallurgical process. And this one using the, you may know, I'm not that familiar with, is a decoder or encoder for artificial intelligence or deep learning network. So what we do is actually we have direct simulation here. When I say direct, I think based on the computational fluid dynamic calculation. And then we take the images for the model to learn, and then trying to actually feed this data to replicate what happened in the model. I mean, this ran about 300 models that we can simulate. This is not additive, but this is a casting for steel. So this is doing a continuous casting in steel. And then you see that the model captured this characteristic in the in the simulation, physics-based simulation, if you want, very well. So we hope we can develop toward this. Without any fundamental model here, we cannot actually get the reliable prediction for metallurgical process that we're interested in. So this is just something, just give you some background. But before we go into the real content of data-driven, I just want to say something about, the buzzword that people saying is, data science and then big data. There are two things that should be aware of. Data science is actually for the next industrial 5.0. I believe that is a backbone for that. So it's integrated, integrative interdiscipline actually that bridge. That integrate over. computer science and technology, mathematics, statistics, and knowledge-based area, which is material science or related area. So that's bring into this big picture. That means you need to work with a lot of people to make things happen. And this one also quite interesting for the characteristic of the big data. Big data is not just the data, but you need to have some, volume of data is important, small or large, or value of data. What does mean, how useful the information you have, and then how accurate and reliable. This is another important thing. What is a type of data? Is that actually systematic correction of data to get reliable prediction or not? It's not just the data that we use for just for the sake of data, but it's not like that. We need to have some knowledge-based screening of the data and then trying to put some methodological background or process engineer into that to get more prediction. And having said that, I just want to open the scene of today with from this paper on the data-driven modeling of process structure property relation in metal additive manufacturing. So you may hear a lot from me that I need to link about process structure property relation. And this is really the case actually for additive to be successful. We need to link all this information together. Not only from the physical model that we are trying to do, but also digital model here as well. So it's in order to speed up or make it data-driven, you need to understand process, what happened in the process level, and the emerging structure. We call, if it's so small, we call microstructure, right, in micro scale. So grain size, grain orientation, grain creation. And then the property that actually resulting from this structure. So understanding of this is something we are trying to do very hard. It's not that easy to link, as you may appreciate in the last few days. But at the same time, we need to close this loop so to get optimization and design and feedback. And hopefully the data that's floating around here will be useful to develop comprehensive understanding of this process structure property relation, and then we can establish some model that can driven by the data that give comprehensive physical understanding. At the end of the day, the industry want quality control of their product, for example. So missing part at the moment is the brain for the machine learning. That as a community here, I believe you agree with me that we need to do something in order to enable some science-based or physics-based or material science or metallurgical based knowledge for data-driven. So in order to do that, this is a conceptual diagram, but if you see for each sub-figure here, this is a data-driven for the process model. I have one example for this one in today's lecture. So what does it mean? You have simulation and experiment data feed in and with the process parameter as an input and output as a parameter that you want. So we try to make data driven for this as well. It doesn't mean only additive as an additive, but we split driven process from each component here. So for example, this one will be, probably structure modeling. That means you have process parameter and then you get microstructure evolution. Whether or not in this one you may have microstructure characterization and learn from experiment is also something we going to look at today as well. So we may have some example that looking at you have some data from experiment, especially a huge data from EBSD or microstructure characterization that we try to extract some feature, learn it, and then driven, and then try to rapidly find out or mine some things from that. Another thing is a property model, which is of interest for many people. So it's the same principle from process to property or microstructure to property. This one actually, some people may process structure and property, but again, there's many people looking at from process to property. Probably the link in the middle can be removed or whatsoever. Again, it depends on case by case, but we are trying to show you some example on this area. So, but it's still some challenge, as I mentioned before, that each process structure and property, even you do some standardization or augmentation here, and then it depends on the complete integration of the data-driven model, who will be the first one who can integrate and show. I mean, yesterday I'm trying to show some integration of cases in the fusion, laser fusion process that you see yesterday. So integration is important aspect. Deficiency and reliability of training data, and this is another thing. So you may need to have some enough data to train and test your model in order to get more reliable prediction. Another important aspect that probably is driven by methodology or engineer knowledge is interpretation of data. So actually this is the part that probably missing quite a lot in, I mean, it just data and data. That mean data is not just data, or the uncertainty quantification. This is something we're talking about, right? It's about the what is a statistic or the distribution of the result rather than a one single point of the result, for example. And then how can we use this property structure relation to inverse design the material or the component to get the part that you want. For example, in AM probably it's more complicated, and it's probably a good example to use for this data-driven process. So just make it a little bit visualized. So we have the data-driven on the left-hand side here. So dealing with big data, machine learning, training, neural network, deep neural network, whatsoever you call it. And we have another end which you see last 2 days here. So we have defect formation, we have microstructure and Melpool mechanistic model, basically. How can we link and make these two more, how to say, talking to each other to create a digital twin for 3D printing? I think we all agree this is probably the ultimate goal for us as a community to drive the technology forward. So I give some example. This is the data-driven framework that people use. This is not actually for additive per se, but it's a kind of additive when you have the deposition of the thin film. This is for that application. So they create the data. You see this one is about distribution of some structure that they're interested in, then try to have a physics base to label or understand some feature which is important. I mean, this is just example. But the next one is actually, I think I will start with the model that we want to make it data-driven. But what I mean by that is this one. So you may know that defects in additive manufacturing is very prominent, and we need to do something on that. And defects, which is actually happen in additive, is happen in the very low scale, micro scale. Let's say this represent, I mean, approximately the scale, and then the defect, which we will discuss more tomorrow in detail in terms of the engineering understanding of that. But today we just borrow some concept of this. So we know this porosity is in the level of micrometer rather than the heat, I mean, how say, the thermal model in finite element calculation. The size of the mesh or the grid size is actually in the millimeter scale. So there's some mismatch between the feature that we are interested in and the defect. Sorry, the calculation element and the defect content is not matched. So we cannot capture that in the FE calculation when we want to do some rapid calculation, right? So what shall we do? That is the next question. So microstructure as well is in the scale of 10 to 100 micron scale. Roughness is also in that palm scale, which is lower than 1 millimeter, I believe, apart from this residual stress or balling effect, which is actually larger than the typical mesh size for finite element calculation. But the lack of control of this, we hypothesize that is depend on the control of temperature that you have to take care of. So the key is that how can we predict the temperature accurately? So what we do, we try to propose some framework that basically try to integrate the information from the lower length scale, like the voice and the microstructure, to the larger length scale through something called more like data-driven, or someone may call reduced order model. So reduce the complexity of the model to a certain level, and then to make it more rapid calculation, and then you can find a way to scale up your problem from millimeter probably to meter scale, something like that. And this is still a conceptual, so we aim to integrate information from the interaction of the laser material and also microstructure and then resulting defect, and try to model something that you can see it moving similar to what you see in experiment. And hopefully we can establish that actually. So this is in a collaboration with some Japanese, Chinese, and also USA as well. So that is the aim. But what we do, we have to understand what we have. So in this is a normal FE or finite element model that you can do in any software, I believe now. So this is purely solving the temperature equation in a conduction mode. So the fluid flow has been ignored. So the scale that they are looking at, there is no interface tracking method at all. And this is based on finite element method on the continuum domain, with powder property is the maximum we can do. So I mentioned briefly yesterday that powder property probably important. It's efficient and suitable for part scale simulation, but missing fluid flow effect. Instead of that, this one actually thermal fluid model, and this is interface tracking method versus a flat rigid liquid gas interface. And then with or without powder packing, it still provides some insight in the scale that we want, that we mentioned earlier in the defect scale, because those porosity is a process in the defect or whatsoever microstructure or the roughness. So it's impossible for the previous model that can predict it. It's more accurate representation, I say, or prediction, but computationally expensive and limit to very few tracks. That's because it's limited by the computational resources you have. So as well, but now probably you can print about 5 to 10 layers without any issue. But anyway, the objective of this actually particular pieces of work here is to trying to build a framework for reduced order. So basically we want a clever thermal model that can take all information of the fluid flow into this some way somehow. So we try to use temperature dependent property of powder materials, and then and take into account the effect of this whatsoever by empirical means equation or analytical equation whatsoever. And then we want to predict some thermal field or history of that, and then trying to understand the thermal mechanical response. And that is the ultimate goal of this one. And this is supposed to be a data generator for our convolutional neural network that we can feed into this data set to train the data, and trying to actually learn from that, and try to establish a data-driven framework that we call reduced order model. So if we see more in detail, here we have the process material dependent absorptivity, for example, numerical implementation of the fluid flow effect, evaporation, Marangoni flow, or convection process induced porosity or micro voice here, latent heat phase transition, heat loss due to whatsoever change, phase change and radiation, natural convection. And this one is established to bridge the gap of high fidelity and the macroscopic simulation. So this is a way, actually a suggested way that we can do and learn from the high fidelity modeling. So the feature is this one. We have heat transfer, which actually, this is a relative main equation, because this is just one kind of more intelligent thermal model. There's nothing more than that. It's just a thermal model, but we try to incorporate some other physical effect on this model by looking at Gaussian heat source here. Whatever heat source you can identify here, but actually this is a volumetric heat source. It's not the surface heat source anymore. And heat loss is follow just Boltzmann kind of Einstein-Boltzmann relation. And then convection with this is normal. Heat transfer coefficients that you know and have to use a lot of time. Latent heat phase transition is actually for powder property as well. You have phase of the gas and the powder, and try to calculate or understand how actually this one is a way to incorporate the thermophysical property. It's just a model that we try to do and then try to take into account the powder and then take into account the fluid flow effect from the empirical relation. Again, this is not ideal, but it's something we do to basically try to take into account this into the heat model and then try to take into account the Milankovitch convection as well in the thermoconductivity of the liquid phase here. So all this thermophysical property, latent heat phase transition, fluid flow effect has been taken into account. And now we try to test something on the two systems, on the titanium 64 and Inconel 625. And then using the property on the right-hand side, you will see that this is a temperature-dependent property, as well as titanium 64 as well from the literature identified here. It's quite big, so we don't put it here. But if you're looking at Ti 64 and Inconel 718, there will be some differences in terms of the size of the melt pool for sure, because yesterday we talked about different thermophysical property contribute to the different heat, diffusion, conduction, convection in your domain. And then if you have with and without evaporation, if you have without evaporation, that means you overestimate the temperature field, and then that means your melt pool actually bigger than the with evaporation. Again, this has to be linked some way, somehow with the lower length scale model to translate the knowledge here across, so you can probably predict something closer to experiment without any expensive calculation. And then we are looking at this as well for different system alloy that actually mostly used in additive manufacturing now, from Inconel 625, 718, aluminum alloy, and the 316 steel. And then you will see by eye, not to do anything more than that. By eye, you see that they're all different size of melt pool. Just the change in the thermophysical property. And this is, again, it's not ideal situation because each material has different optimized process parameter, but we just show this for the sake of comparison that you will see that, aluminum probably melt a lot, and for example. And if we try to make this one more predictive, we try to calibrate now with available data. You see that we use the mesh size quite small here, and then you see the melt pool here is actually in the size of 200 to 150 micron. And if you going back to literature from SEM, TM, or SEM optical microscope, this is in the size of the melt pool that we see in the experiment as well. So this is the dream that we want to have that quick, but not very quick, I would say, at the moment, with just a single laptop or workstation that we work on here, that we can capture some of the things that probably similar to the experimental measure data. But that does mean this is one attempt that we try to study this for the dependency of the property. And one additional aspect, we can do multi-track, multi-layer AM. That means we can deposit whatever you like, but now layer 1, layer 2, layer 3, layer 4, and layer 5 here. And then you will see that the melt pool is not actually the word that we call steady state. In welding, probably you can say steady state, but this is because the heat beneath that actually contribute to the size of the melt pool for the next layer and next layer whatsoever. So there is no such a steady state in additive if we not control it very well. So this is one message from this slide. And then if we try to understand this signature of the thermal signature a little bit, we build this 1 by 1 millimeter cube here, but we can extract classic thermal signature for different layer here, for different material as well. And then what the information from this is quite useful, that I will have some example a bit later, saying that this peak temperature is important in so many ways possible that we can think of. But this is one example that we can see that, one question that we can ask from this model can tell us quickly how many layers beneath that this material has been remelting. Example, there's some characteristic that nickel probably 3 layers, but titanium probably 3 or 4, but aluminum probably 15 layers remelting every time at the optimum condition, for example. So this information also important for developing a further model as well. So we quantify this alloy dependency of the melt pool dimension as well. You will see as a bit different, apart from this aluminum, which is behaving so differently from others. And then you can characterize and get some feature that actually, CFD people trying to predict. So this melt pool size of material and process dependent, and is affect the microstructure evolution and part quality that we all know. And this has been validated against the available data at the condition investigated here. So this is a temperature field that we use from this paper here. And you will see the prediction and the measure of the melt pool doesn't make a big difference. So that means the model is reliable at some level here. So, but the next step for us, you will see the model doesn't taking into account the defect which is formed during the process yet. What is a statistical approach that we can do to approximate the defect which is formed? Because the formation of the defect during the printing also important to make the model more reliable. And then we trying to capture this based on this is simulated defect, which we will talk more tomorrow. How can we get this distribution from the CFD model? And then we try to do something in the MATLAB to generate kind of the same defect with the same distribution. So that the information translates across is statistic from the process, either from model or from experiment. And somehow you need a numerical approach to actually translate this across your calculation domain to capture. For example, this is a conceptual idea that the color bar here show red means more porosity. So somehow this will impact your residual stress and some other property. So this is probably the first step. We actually define the defect based on the data from lower length scale model or experiment, and then identify this thermophysical property that replicate the presence of this defect. In this case, it's a void small pore. So if we just prove the concept, we have only one defect here, present only one porosity here, and then we try to see the effect of this. You see this is the thing. I just see if this is a moving. Okay, no. And you see one porosity actually increase cost of computation. This is something that community needs to discuss and try to move forward. With and without pore, the peak temperature has been shifted by this. So this is something to consider for the accurate prediction of the temperature. I will have some slide talking about how important of this in a bit later. So, and the next step, once we do this and we believe this is good, so we can do data generation algorithm from that. Rapid calculation, I would say, what I showed you before. And then we generate this data combined with some understanding from the our previous CNN model here to capture this is the measure and the predicted here. We try to do the same here using the CNN architecture that we learn the data and process parameter, laser deposition pattern whatsoever, and then use some deep learning to get predicted temperature field. Again, this based on the image that you get from the result, or if you want to do like extract from the coordinate in the data is also possible, but it depends on how powerful of the code you write to make this possible. Yeah. So just summarize in the first part here is that reduce all the model, we try to bridge the macroscopic and high fidelity simulation. It's easy to actually implement in other material systems. It's not just what I show you here. And we hope that the data generated from this model is a model generated data, can train CNN model that can we complete the how to say, the data-driven model here. And we hope to do the physics-based thermomechanical model that can develop to couple this with mechanical analysis. Again, there's still a lot of work to be done, but this gives you a kind of beginning of the picture for the data-driven model. But we want to do something more fancy. That is the path scale analysis, but this data-driven model also used in the Melpool length scale as well. What happens if we don't want to run the CFD now, but we just want to have the data-driven to represent what happened in CFD simulation, Melpool simulation. So this guy, I mean, in the, I think, University of Pittsburgh, proposed a framework called Computational Fluid Dynamics Impulse Finite Element Method, or CIFEM. So what it does is here is actually they try to learn from the high fidelity model using this envelope called CFD impulse zone, which actually just capture what is happening in the Melpool moment, and then try to solve the heat equation. I mean, after that, after they run the CFD, they generate the CFD using the, I think, Flow 3D, and then they generate, after they get this data, they extract this one, trying to how to say, digitalize the result, and then using the solve for the heat diffusion by Newton-Raphson method here, and then trying to deep learning FE model process. And then what they do, they get this data to train the model under the framework called CIFEM, and see how good or bad that they can predict Melpool simulation in detail without using CFD calculation. So this is what they do. So they have CFD data feeding in. This is for heat source model, and then they have encoder and decoder to predict the thermal field here. I think this is based on the images, and then they use this CIFM interface to predict model thermal field as well. So the key feature is that this is just 2D transfer CFD thermal field is provided to this encoder FT that encode each 7,800 dimensional input into this 20-dimensional latent representation. And the decoder G here is denote the learn latent representation back to original input and combined network. So after that, they train the neural network model here to minimize the mean square error. Again, I think I don't need to repeat much about how neural network work. But the good things of this is actually they try to do something on additive. So this is the kind of, this is a time interval epoch loss history for training and validation. You see that it's quite good fitting both model actually for deep neural network and autoencoder here. And this used to predict the Melpool size worth of the CFD FEM used to predict the simulated Melpool size and compare with experiment. You see it's not too far off from this actually kind of Melpool size. I will show you more insight a bit later. This is a size dependent of this 20 different process parameter. So they train across these different parameter. But now another one is they want to make model more generalization. So they train this one with unseen process parameter and see how good or bad of this model is. So that means they can capture somehow, but not as good as before. But it's the accuracy of this is quite acceptable, but not ideal. And if you know, if you see here, after that, they try to understand it. As I said, this is a transient CFD import zone algorithm for longer scan track. So they capture, they only using adaptive match only this zone to capture this one and neglect another zone. Again, this is another computational numerical technique that not many people have. So this is developed with a big company that they can do a lot of calculation here. So later they use this model to compare with different, I think this P represent different process condition, compare with the available, CFD model that they run. So you will see the differences is quite minimum from the CFD, which is heavy calculation, and the neural network calculation that they have. So CIFEM precisely. And this is what happened. And then just compare what you see. This is CFD. You see a lot of oscillation, ondulation at different condition. This one is different condition here. And then they see with CIFEM, it's not too bad, but it's actually not the same. For sure, you can see there's some differences. And if you, ideally, you want to have something even simple, so it's just a Goldach equation here, just volumetric heat. It's actually not very good, but they capture something. But you cannot get, you don't have any depletion zone, you don't have any oscillation of the things, but okay, we try to ask ourselves whether this kind of model is good enough for us to drive the technology forward. And then we compare, they compare as well, not we, they compare as well the thermal field with the size of the melt pool. Again, you will see that the CFD kind of model is probably the best match. I mean, this is the quantification of that model. You will see how good or bad, deviation of this model to each other. So that is a good step forward that they train about, I think if I remember correctly, about 800 model here or a condition. So it's a large set of data. And this is just give you an impression that the total parameter here is 13 million parameter, 13 million parameter. So contractive and auto-encoder network architecture has been used to get the result you just seen. And the deep neural network architecture here, they have a parameter about 400,000 parameter here. So it's not easy task. It has to be collaborative. It has to be something that we want to move the technology together. This is another thing which may interest to you, which is data-driven analysis. Again, this is analysis for the process structure property of Inconel 625, Inconel 718 thin wall. But this one is not pattern-based fusion, it's a direct energy deposition. But I just want to show you how they do this data-driven framework here. So what they do is actually they try to deposit the thin wall of Inconel 718 to capture all aspects from processing structure and property. And this is what they do. They have the infrared temperature measurement at different locations. So as I told you before, each location has different thermal history. So they extract this thermal model here, validate with the imaging, IR thermal imaging, and then get the analysis for the cooling rate and sulfication rate to property prediction. I will tell you what they did. They actually do predict UTS, yield stress, failure stress, modulus, based on the thermal data they get. And this is, they use the 1D convolutional neural network to extract those features. Even they can predict some primary dendrite arm spacing, which is important for the property later as well. And this is how they actually define the domain. So this is a thin wall with the infrared camera here. And then they have 3 cases, which is actually smaller build. There's no dwell time here. So that means each deposition is go on, all together, not leave some time. But case B and D is a bigger build, but one of them has 5-second dwell time before the next deposition. This is something what you can see. And this is the model that you can see, simulation versus the experiment. You see there is some mismatch in the, case C, but it still capture the trend of the thermal cycle. And why this is important? Because thermal signature here is something like this. Just one, you have some, some time between solid dust, liquid dust temperature. Just a characteristic in additive manufacturing is happen like there is no smooth curve like that. But this is what happened in real life. This is what is the complicated thermal signature, as I said. And then you can count here before it's actually solidified. There are about 5 layers that melting down the substrate. I mean, below underneath the layer. So, and then this A specimen has been carried out to compare simulated and experimental thermal history. So you will see at different location as well. So this one at different 12 and 8 location here. So what this say, actually for case B, when A, B, and C is as follow here, you see the microstructure that result from these things are different, and they have different cooling rate. As such, they get different primary arm spacing, and then they can calculate approximately the Raoult's phase, which is a detrimental phase for each condition. So they can predict UTS, U stress, fraction failure stress, and also modulus here as well. So if we are looking at the specific condition on case B, which is a bigger build, 120 millimeter at 3 locations here, you see the microstructure is not the same, 1, 8, and 12 here. And then these contribute to different property set as well that they can predict here. So it's quite encouraging actually that the data from this data-driven can provide such an insight in a rapid manner. Again, you will see now data-driven is not just data, it's meaning something for the manufacturing process. That's what we want actually. So they characterize or analyze the primary arm spacing as a function of cooling rate, because this is something, if you are metallurgy or material scientist, this will be very important aspect to understand, because this will tell you a little bit more about the defect which is formed and in the later stage. And this, actually, there's some correlation of the so many cases that they run. Again, impossible without any neural network. If you want that, we can relate the temperature, field, and mechanical property. And I will show you later that. And you will see here the temperature field or temperature, peak temperature has an influence on the property significantly. That's why we have to control this one. And then based on this scene and structure with the intermediate layer visualization here, in different conditions here, you can actually predict the UTS, compare with the CNN model, measure and predict it. And then you will see the training data is quite well, and the test data is actually not too bad, but it's not ideal as well. But at least we get something rapid recalculate. So next one, as I promised, the data-driven model is not just the model and identifies its use. So now if you are experimentalist here, you may question me, what is the machine learning that enable autonomous microstructure characterization in 3D printing? So this is what happened. So they try to build a model that used for real material characterization. So this is the ML method for autonomous microstructural characterization in 3D polycrystalline material. The first one is probably this image is from the correlative microscope that you get the 3D structure of this. So you first write an algorithm to identify the local structure topological classifier here, and you voxelizing the process efficiency based on the image you have, and you try to, again, these all are numerical or statistical technique that you do to basically, thresholding the boundary actually, and then clustering the algorithm and improve refinement because the boundary here is quite stepwise. So you may need to smooth out some microstructure and then optimize back to get this one for example, if this is for atomistic calculation, if you like. So this method has used to represent different crystalline material in metal. It's not just nickel-based superalloy. It's also used in the aluminum alloy FCC, iron, silicon, and also titanium as well. So you see that the size of this is quite good that they can learn and then represent the structure in 3D. And what it's used is about to get the predicted grain size with the actual grain size in the Inconel 100 nickel-based superalloy here. This is unsupervised machine learning method for the grain identification here that you can replicate the serial sectioning in experiment. Again, this is important. As I said, the microstructure is important for the property that are coming together, that away from data-driven simulation that allow you to replicate the structure quicker, faster, but minimize data storage, for example. So this one, I think I'm a bit fast again today, but I think there's some detail that we probably need to take care of in terms of the understanding about the data-driven, and also not data-driven is not just image analysis to get something, but we need to, as a community, need to use this data-driven approach to do something which is useful or meaningful for engineering application. And I think if we go back a little bit, I just want to spend more time on this one. I think that what is the thing I want to emphasize as well is actually we said that now the in-situ monitoring is quite important. The thermal history is the backbone of the future technology. I mean, people here may have the thermal imaging things that you may see here is a temperature prediction from model and the high fidelity modeling. And these actually contribute greatly to the prediction of the defects underneath the, during the 3D printing. As you see here, this one can capture, but if you imagine if you can combine this to the way you do this one, which is in another additive manufacturing process, and then we can actually get the relationship between temperature and mechanical property. And this is a perfect scenario that we want to basically predict as a function of cooling rate, and then you will see you have the property which is actually has a correlation, I would say, or have a correlation with the UTS, and this is the ultimate aim that we want to get. Another aspect that I want to emphasize is that there is stochastic process. So we're trying to predict the trend at a statistic, the distribution, and also the noise of the process that we want to reduce as much as possible to control it. So the way forward is to control the the noises in the system that can allow us to do the quality control of additive manufacturing for specific material, machine, and process condition we want. I think probably I want to open for discussion now. If you want to ask anything regarding this, yes, please. Otherwise, I may have to have another.
Sir, actually, you had shown one slide that with without the evaporation and with evaporation, there was reduction. With evaporation, there was reduction in the size of the melt pool, right?
Yeah.
So I would just want to ask, with evaporation, there will be is evaporation during the evaporation, there will be vaporization of the elements. Okay, they will take away the heat from the melt pool. So will there be reduction of the temperature of the high peak temperature of the melt pool as well? during evaporation will also reduce?
Yeah. When evaporation, evaporation here kick in, because if you have the normal diffusion, thermal diffusion equation, when you solve it, it can go to the ridiculous number like 10,000 degrees centigrade, and this is not realistic, because nature not allow this to happen, because once you get to the boiling temperature, there will be some dissipation of the thing. So the temperature usually never go up to the boiling temperature. So we'll damp that temperature down due to the, what is called, due to the latent heat that we need to damp the temperature down. That's why the heat contained in the material actually lower. And that means once the energy here is lower, the size of metal pool is smaller. Your question is?
So in this case, in the legends that we are seeing over here,
Yeah.
both the legends, the peak temperature is somewhere around 3200 Kelvin, 3200 Kelvin, both these legends, with and without evaporation.
Without, it's about 3,000 Kelvin, which is around the boiling temperature.
I'm just asking whether the temperature will also, peak temperature will also reduce in case of evaporation, when we consider the effect of evaporation.
Yes, if we consider evaporation, peak temperature will be reduced.
Reduced. Okay.
Yes.
So, but there.
Previously, it's overestimate. If you don't corroborate evaporation term, this will be overestimate your temperature.
But there, what in the legends it was shown that in both the cases the peak temperature was near about 3200 Kelvin.
Which one?
Back slide, previous slide, please. Previous slide. More. Yes, over here. Yes, over here. In both the cases, the legend, as per the legend, it shows that the temperature is
Okay.
3200 Kelvin in both the legends.
Okay. Okay. How to read it? This is something to be careful. So that means that the top one is actually blue, right?
Yeah.
That means any temperature above this one is also blue as well. So this doesn't show absolute value here. It just represents that temperature above 3,000 something, it will be blue. And then you see the blue region here is larger than this one.
But the legend would have scaled as per the highest.
Yeah, sure. That's correct. But it is actually around something ridiculous number like 10,000.
Okay. One more thing. So you have discussed this thing like using deep learning architecture, GIAN and other things with this CFD model, right? In some slides. So how can we incorporate physics-based loss function within the means what kind of physics in case of welding analysis or laser powder bed fusion we should consider to incorporate physics-based loss function within our deep neural architecture, means CNN architecture or something like that. Physics-based loss function. Typically we use means already available from TensorFlow or Keras. We use loss functions such as
I'm not sure I'm not sure understand your question correctly. But
so
if I'm trying to answer your question, I understand that you're asking me how can we incorporate the physics based loss
functions
in the machine learning. So what I show you, probably the next example, is actually we learn the data from physics-based model.
Yes.
You understand? So it's basically image analysis, just image analytics. Yeah. So that's what it is. So that means that result contain physics already. But if you ask me in another, probably not in this case, if it's actually applied to some, for example, alloy design using data-driven as well. So you may need to have a kind of equation to incorporate the physics into that. Again, that is not applied in the example I show you. It's just that learning from the data generated from high fidelity model in this case, yeah. Otherwise, you have to find a kind of a numerical framework that incorporate the lower length scale information to the large length scale like this to get the rapid calculation for the model. Again, this already taken into account physics, which happen. So it's number of ways to do that, but I think your question doesn't apply to my talk
So,
at the moment. Yeah.
okay, but it typically people are working on physics-based this deep learning architecture where they use Navier-Stokes based loss functions into their model.
Yes,
Yeah.
that is another. I understand that, but that means they want to run separately the model with the taking into account the physics base whatsoever. There, that's also a way to do or generate the data as well.
And one more thing, you had shown that Golduck volumetric heat source,
Yes.
it was not able to predict the temperature fields much better compared to the CFD based model, right?
Yeah.
So if in case if we replace
mean
the Golduck
Golduck? Yeah.
volumetric heat source,
Yeah.
if we replace it entirely with the conical heat source distribution, volumetric heat source distribution,
Yeah.
so
In
that
principle, we
might
can,
be comparable, I guess, right? Means I
we,
just
we
want
can
to
try. I also but I believe they also try as well. But probably this is the best match. I mean, analytical equation that match. But it's not ideal, as you know. This is if I want to comment on that work, that means they do only one track, right? What happens if you do 2 track, 3 track? This will be different again. You
Okay.
see, and I'm pretty sure analytical solution cannot capture that.
No, I'm
Yeah.
not talking about the
Yeah.
analytical solution. I'm
But
just
you
concerned-
you asked me if we compare with different heat source model. That's what you
heat
asked. me.
source model,
Yeah,
just
yeah.
heat source distribution that is being incorporated
I
into.
think probably a good trial if we can come up with or using the learning to come up with a new heat source model that represent this data. That would be a good idea forward. I think.
Okay.
That means we only deal with one equation, right? That we can use for simulation, rapid calculation. That's what your question, I
No,
believe.
actually, I was not asking about the analytical solution. I was asking whether within in their case, they have included Golduck heat source or volumetric heat source within
No.
the file. Huh?
No.
They haven't
What
used.
does this mean? Include? They just use that to compare under condition that they simulate with the CIFEM and then CFD.
Mhm.
Because that is basically the equation, right? That I show you.
Okay. Okay,
I'm
thank
not
you.
sure.
Okay, I will ask for it. Okay, thank you.
Thank you. I understand this is the one you asked, right? Why you said why it has to be this one or?
Actually, they are using Golduck heat source model, right?
Yes.
So in that case, if we are going to use conical heat source distribution,
Yeah, you can.
it can be comparable. It could be comparable to CFD, right? With CFD result. In some sense, if we just want to compare the thermal.
Yeah, of course. You can have another column here with another conical heat source also and see if how comparable. That's what your question, right? Yeah, sure. Thank you. Yes, please. Yes.
Can you please explain a bit more about the reverse engineering part?
Say again.
Reverse engineering part, like there was a one slide, right? In the previous slides.
Pre-
Reverse engineering.
this reverse engineering one. What is the
Yeah, next one.
this one?
Even that. Back.
Back. Very first slide.
This one. Next step. Yeah.
Okay. Yeah. What your question?
Can you please explain a bit more? Can you please explain a bit more, like how it's working and all?
Yes,
To elaborate.
yeah. So just want to show that they have the inward and forward design. As you know, it's probably better to make it look probably this one is the same thing. So basically you have this is a forward design, right? Straightforward from process, structure and property, and inverse is just from property that you can decide what is the process that what is the property that you want that process condition that will produce that. So you reverse sorry, inverse your design here. I just showed an example here that this is the target performance that they want. So they inverse design from the target performance or property here, and then they try to decide what is the condition that they need to make it. So it's the same as my very first slide on saying on additive that we need to understand the process to design this one. So but basically this framework has been used for thin film material here. So just this is my point, that's it. Yeah, so basically from this one, not only additive, other people also doing the same as well. But as I said, I want you to appreciate that this is whether or not they get some synthetic microstructure here and then doing some learning here. I think in terms of the principle is pretty much similar, but the detail are so different because we are looking at different probably feature, property, or whatsoever. Yeah, thank you.
I just want to know how the physics is captured in all these models, whether it is like using the PINS model, like physics-informed neural network, or some analytical models in capturing the physics of all these from the microstructure level to the property correlation, structure property correlation.
You mean if we use the machine learning based model, right?
Yeah, physics-informed neural network or something like which includes the physics last term to capture the physics-based
yeah, it's
approach.
probably a similar question as you. I think from here it is learning from the result from the model, from the high fidelity model. But if you want to have the physics-informed neural network, it's probably applied to, for example, alloy design, another thing. So that means one of the way we do it, we use the inform it from experiment. That means you may extract some empirical equation, simple, one line, feeding into the neural network algorithm, or you extract the relation from, let's say fluid flow from model, again, simple, analytical, or one equation into that. That is how I see that people do the linkage as well with the physics, or we call physics-informed model. And that means before that, you may need to use some knowledge from material or engineering to screen the data. So the data is not just the data. If you have 1 million of data, we need to find, knowledge-based screening and then clustering before you training and blah, blah, blah. I think tomorrow we'll have an example that they show in some cases we have to cluster between different set of data. Let's say this belong to one grain or this belong to another grain, for example, in the microstructure level. And it's a combination. Definitely, that will make your neural network or machine learning more clever, right? And this also apply in our alloy design algorithm as well, that we use some methodological understanding to inform the data-driven model that we show on Friday. So yeah, in short, deduce your relation from experiment or the model with a simple explanation, feed into the neural network. Again, this will increase your calculation time probably significantly in the neural network, but it is probably worth doing that. With the assistance of the computer scientist, we may try to make it quicker. Yeah, but anyway, that's probably your question, right? Sure.
Sir, can you go to that can you go to that melt pool thickness slides? The comparison of some 5 different materials you have shown. This one, sir.
Yeah.
So here we use constant power and laser speed for all different materials. But
this is for the sake of comparison.
But in reality, if you take aluminum, that is a low melting point material, obviously we'll choose lower power. So in that case, if we keep higher power, Inconel, it's obviously high melting point material as compared to aluminum. So definitely
understood.
So then how representative these models are like? is it okay to compare with this same laser power and
Understood. So that's why I said at the beginning that this is just for the purpose of comparison. But in reality, we need to optimize. We need to select optimized condition for each material to simulate. But for I mean demonstrating the thermophysical property dependency of this process, just for visualization, this is what we see. And then I appreciate that these three have the similar kind of melting solid at liquid at temperature, but not this one. But yeah, you are right, completely correct. But this is just for comparison. Yeah. Yes, please.
Or have the data. So usually we go for those high fidelity tests, but they are also based on some physical model which have some assumptions, and they are usually like they are away from.
So you said high fidelity model.
Yeah.
What is a high fidelity model different from physical based model? What is
No,
the
they are the same.
Yeah,
They are
they're
the same,
yeah.
and we usually take data generated from them to train our data,
Yes.
the data-driven models.
Yeah.
But usually they are away from the reality or from the experimental data.
Yes.
So usually we get asked this question that why didn't we use the experimental data to train our model, data-driven model. So what is your take on that? How do you like answer this question, or how do we?
I think, yeah, this is a very good question. But in my opinion, it depends on what you are looking for.
Yes.
Let's say if you are looking for microstructure prediction, for example, definitely, probably at the moment, only the data from experiment which we generate a lot can be more reliable to use for the training, which is true. We have evidence that. But the problem of this is that if you collect this data from different conditions, different places, they may get some, how to say, inaccurate.
They have biases
because
there.
bias.
Yeah.
So it's actually not systematic correction. This is another question, whether you can get a systematic data that we can use for reliable prediction. This is the question. But modeling definitely is more systematic in the sense that you know what to do, right? And then you start generating tons of data, given your resources around, for example. And again, there's this something that we need to work together to make the prediction from the model closer, because that means you will remove the necessary to do experiment. And that is the goal, right? We don't want to do expensive experiment for some expensive material. We're trying to make the model as intelligent as possible to do that. And that is the goal. So I hope not too far from now, we can get that point. In some cases, we can show that probably model data can have predictive capability. But another aspect of modeling that can provide you is to predict some feature which is difficult to experimentally measure, like fluid flow pattern, for example.
Thermal history is also difficult to measure experimentally. In situ.
Yeah. But some cases, if it's not in this metallurgy field, it will be in CFD, for example, fluid flow in the flow of the airplane, something like that. So that is something not easy to measure, right? But if you can find a way to rapidly calculate without doing direct simulation, that would be good. So again, my answer to is depend on which application and what you want to do.
Thank you.
Yeah, here.
Sir, while modeling the thermophysical properties,
Yeah.
so we use standard data, right? So that are taken at a
Exactly.
standard rate of temperature.
Exactly.
But when it comes to additive manufacturing, the rate of heating and cooling is so high.
Mm-hmm.
So are we considering the kinetics while taking the thermophysical properties?
Very good question. I think this is another area of research as well, thermophysical property. So That's correct, because we rely on what we have at the moment, right? And then we try to do something about it using some, we believe we're using some kind of this, what I told you before, so fraction of the powder, and then you believe that this is the bulk and the powder property will be following that. Again, this is assumption. So we don't know whether this is correct or not, but we hope from the previous understanding, this assumption actually better than just using the bulk property, for example. Again, the bulk property here is actually come from different metallurgical process. You will know there's some differences, and these differences may be important to the predicted peak temperature. Again, hasn't been very fully investigated yet, but there's some commercial software packages trying to make some new database for AM or powder, basically. I think you know about that. So yeah, I think this is something to research and do more. It has to be experiment, because this is something. Otherwise, you have to run first principle calculation, quantum mechanics kind of model to get this, but it's not ideal to do it because it's so expensive as well. Thank you.
Any other question?
Yes, please. Yeah.
Sir, you mentioned that one, yeah, finite element methods, continuum application, continuum mechanics, that one. So is there any case study on that also? Because continuously we have a
Which one you said?
finite element method properties, material properties. One slide was there. FEM.
This
no,
one.
other one. So one slide you have mentioned that one state in the initial
In
starting. FEM based analysis.
this one? Oh no. Oh, okay. This one. No, the next one, right?
Initial. Starting like.
No, this is the one.
In the one statement you have mentioned in the initial slide, starting classes, like that IFM one case study, you have one elaborate explanation on that.
Okay, let me go to that one. So we understand the same thing. This
Next.
one.
No, FEM statement is there in the data also.
Which one actually?
Let me, I'll show you, sir. In the
This is the first slide.
next.
Next one. This is my.
Next. Okay, I'll show you, sir. It is there in the book. One finite element method on continuum material desired properties.
Yes. Anyway, can you ask your question? Yeah.
And what? How do we catch that weld pool size while printing? Exactly that whatever you have shown the weld pool size numerical model. So while printing, that weld pool, whatever laser speed and temperature, and we can capture it. That weld pool, whatever the size is there, 210 microns, you mentioned. So how can we accurately calculate that one, sir? Experimental. Is it possible?
Yeah, there's a lot. I mean, yesterday I showed you the measurement of the temperature that people trying to measure the size of the melt pool on fly. That's been doing the deposition. And that's what your question, how can we accurately capture?
Yeah.
This is another research for institute kind of monitoring people. So they're trying to find a way, because they said the infrared information is probably somewhat over or underestimate the melt pool boundary. I think this is the technique that related to the instrumental things. Again, I think, as far as I understand, they try to use different kind of way to capture it. Whether you use thermocouple, which is very more reliable for engineer, right, to validate against. But it's impossible because this is a melting process, and it is, yeah. So the way forward, as far as I understand, I'm not I don't know much about this area, but my colleague does, which is from Imperial. He will try to find a way from the changing the heat source as well, or camera as well. So they have different model of camera that I can't remember exactly, but that is to interpret the emissivity from the camera to get better representation of the temperature. But still, some people in some lab also quite reluctant to say this is a temperature. They just say that this is the melt pool boundary. Don't talk about, but that probably enough for us to move forward, because the melt pool size is important for microstructure and other things development. And then you can say that if you know melt pool boundary good enough, again this related also to the resolution of the camera. What is the spatial resolution, right? If it's so rough, so coarse resolution, you won't be able to define the boundary clearly. And anyway, this melt pool information will be important for microstructure and property later. So this is what I see. So in short, that means instrumental or in situ monitoring system may need to be implemented, make it more reliable for us as well as a modeler. We need reliable experimental data to calibrate, to validate with. Yeah. So yeah, that is something that people in this area may need to do experimentally. Yeah. Yeah. So we did it in a number of ways. For example, we are looking at previously, before we show here, we use thermocouple at the substrate of the material. One thing. Second one, we use synchrotron imaging. Again, synchrotron people, even they know in the melt pool length scale, now you are zooming in the melt pool length scale, they still reluctant to summarize that this is the temperature that you get, but they later said this is the emissivity profile that you get. So like that. So I mean, this is a way to represent thermal field, but we cannot probably say for 100% sure this is the 1555, something like that. But just a qualitative measurement at the moment, as far as I know. But someone tried to claim as well that this is the temperature, but it's based on assumption anyway. Yeah, that represent what happened. Yeah. Yeah.
Professor, would you please go to the thermal signatures slide?
Say again?
Thermal signatures. Not this one. Next one. Yeah, this one. Backward.
Oh, this one.
Yeah.
Okay.
So this is a simulated thermal profile.
Simulated.
Simulated one.
Nothing doing with experiment at the moment. This slide, yeah.
Yeah. So how to accurately get these thermal signatures, simulated ones, in comparison with the experimental thermal profiles? When we see the experimental thermal profiles, the pattern is slightly different, and this seems to be an overestimate of the temperatures, right? In the layer 2, layer 3, layer 4, if you go, the temperature is increasing, whereas the general trend is it decreases. As
okay,
we go.
I need to tell you, we are sitting at the same position when we measure the temperature. Yeah. That means this position experience, that means this one, I'm staying at point A here.
Yeah.
I'm still here, even they have the second layer.
Right.
That means this temperature experience lower temperature when you pass. Whether or not this will be remelting of, you see, I'm not following the path. I just stay, let's say, at the base of the material.
I agree. My question is, I understand the peaks A, B, C, D, E.
Yeah.
The temperatures go down as we go to the next layer at the same point.
That's we are at the same point.
But the baseline temperature, the baseline temperature, the trend is in an increasing mode, whereas in reality it is a decreasing mode.
Understood.
Then we get an overestimate of the temperature, is what I feel.
Understood. I think you spot the right point. Yeah. So I agree with you.
So what is the parameter we need to change here so that we get the realistic trend more?
I think what we are looking at is probably transfer coefficient at the substrate. That maybe suck some heat out of the domain. But again, this is still need to be improved. As I said, we try to develop a framework using those empirical relation here, or from modeling here to basically show the proof of concept what we have. But anyway, you are correct. Yeah, it's expected to be like this, even it's slowing down, like I show in schematic diagram. Yes, sure. It's also contribute to that as well. You mean the well time, I mean, leave some time before deposit the next. That's also what we consider. Yeah. Again, this has to go hand in hand with experimental list to see what is the real representation for the situation. Yeah.
Yeah.
Agree. Completely agree. I think his point is this actually. This is why this is a little bit increased here. Yeah, but he said that in reality, probably I mean, in order to capture what really happened, I also agree with you as well that under assumption made, this is correct, but in reality, if you compare, it will be this kind of temperature. It will increase first, actually, and then decrease, right? This is a measurement, experiment here. It will increase first and then decreasing. This is from experiment. Again, but again, how you trust this IR imaging, this is another question. Yeah, so this is increased first, and I understand, and he also correct. Yeah. No. Yeah, but you see here, first few layer is increasing. Again, I said after that, we need to calibrate with experiment carefully. So nothing wrong with the model as well, but we under assumption made is correct based on that. But yeah, thank you so much. Any other question? I think I like the session like this, that we generate some discussion and then.
For the better understanding of each other, can you please, in a quick way, so what you are doing here?
Yeah, introduce yourself. I don't know you. Yeah, okay. I am experimentalist looking at instrumental whatsoever for male pool, something like that, or you are metallurgist looking at the alloy development. That would be great.
I'm a mechanical guy.
Yeah.
I'm not a metallurgist either, nor a metal scientist. So definitely the perception which it will vary.
Yeah.
For the better understanding of each other, so may I request in 1 or 2 minutes quickly, so yeah, introduce your work, so better you can understand.
Yeah. Who? So in the meantime, just want to say that in the next 3 hours, I mean not 3 hours, more than 4 hours, right? So next two sessions will be about the training from my postdoc. He will join online. I don't know much in detail how to do setup and everything. He aimed to show 6 cases for the ANSYS fluent that we implement for additive manufacturing. So please do ask if you have questions, but we aim not to go over the scheduled time because of we have other activity as well. Yeah. So probably 3 cases each session. Yes. Yes.
Sir, good morning, sir. Myself Swaminathan. So I'm
where are you from and what are you doing?
Yes, yes. So I'm an assistant professor working in PSG, Institute of Technology and Applied Research, Coimbatore.
Yes.
Sir, recently we started working in the area of metal additive manufacturing. So
metallurgy.
Metal additive manufacturing.
Right.
I'm basically
which material system you are looking at?
Yes, sir. One is aluminum silicon 10 mg.
Right.
So in which using thermal imaging system,
okay, you are
we are trying to
experimentalist.
powder bed, sir.
Okay.
Powder bed. So we try to using data-driven model. We are trying to address the porosity related issues. So we try to optimize the process parameters based on the porosity, minimization of porosity, using thermal imaging analysis type.
Right.
So that is one part of work we are working. We just started working.
Right.
And the other work, which is basically modification of in-kernel based powders by
Okay.
adding yttria and yttria stabilized zirconium.
Which ink canal you are?
718, IN 718. We do
You know
some.
there is someone in Sweden also doing similar thing, I think, with the changing some, I can't remember, some element,
Yes.
vary percentage, and you want to check the printability of that, right?
Yes, yes, yes. So it is similar to that. People, they do some coating of yttria on in-kernel. So what we are trying to do is, instead of coating, we'd like to impinge the yttria at a nano level on the surface of the in-kernel powder. So we use that as a raw material for additive manufacturing, and we'd like to see how the material behaves, how the corrosion property. We are planning to do these kind of studies. So currently we successfully able to produce the powders with surface
Very good.
modification.
Very
So
good.
next step we are planning to go for
Printing.
additive manufacturing. Print.
Yes, sure.
Yes.
Anybody from IT Madras? Yeah, please.
I'm Sriram and I am from IIT Madras. And this is my first semester and I am PhD scholar at Department of Engineering Design. And I'm doing my coursework currently. Currently, my professor has given the topic on the fatigue life prediction of the additive manufactured components.
Fatigue life
Prediction. So using the fracture mechanics approach and
Very
defect
difficult,
modeling, like
yeah.
the pores, lack of fusion, and keyhole formation in the additive manufactured components. And I aim to model these defects and how it is going to affect the fatigue life of the component.
Okay. What is the fracture mechanics framework that you use for your fatigue life prediction?
No, I have to do some more literature review on that. So
Okay.
this is my just my coursework.
Okay, sure.
Good morning, sir. Myself, Maurya. I am Master's Research Scholar at IIT Madras from Engineering Design Department. I am working on developing digital twin for autonomous factory, which involves a 3D printer as well FDM printer. So I am trying to predict the defects from the data-driven and physics-driven modeling of the FDM printer, so that it is helping us to identify defects within the factory setup and give a control feedback to the machine to rectify them in real time. So that's what I'm actually working on.
Very good. So you said automation or
Autonomous factory.
That mean will be robot.
Yeah, robots are 3D
So it will be
printers.
DD process,
Yeah.
right?
Yeah,
Direct
like-
energy deposition.
No,
Why
like
the-
in our factory setup, we have multiple things. Like we have a 3D printer, 6-axis robots, CNC machines, and all. Like
Okay,
we
sure,
have a
sure,
test
sure.
bed of factory setup, and out of it, I am
Okay.
working on the 3D printer digital twin
Sure,
development.
sure. Thank you.
Just want to add a point, like mine would not be related to physics-based and data-driven modeling for the remaining life, RUL, remaining useful life prediction of the component.
Thank you.
Hello, my name is Saurabh Tripathi. I am a PhD scholar at IIT Kharagpur and I am working under
Kharagpur.
Professor C.S. Kumar. So in our lab, basically we have EOS M290 with in-situ monitoring setup. Actually, we had this machine since 2009. And
Right.
earlier, we were actually in this in entire country, India, we were the first one to have this machine, and that too because of one of the visionary professors.
2009 you're talking now.
No, it was earlier 270, and one of these research scholar actually he had mistakenly damaged this machine because he was trying to process copper. So
Yeah, challenging material.
yes, so it was very reflective, and it got entirely that laser system is down. So we have kept it in our separate lab that still
Yeah.
US people
I
haven't
suggest
picked
you
it up.
use the same technique as him, coating the powder, but anyway, later.
So later, currently that guy is currently professor at IIT Delhi. So in our lab, earlier people used to do a lot of experimental stuff like surface re-engineering using the same, because the chamber itself is having a controlled environment, so
Yeah.
it allows them to do various kinds of stuff. I have been this before me. There was one more guy. He started doing this thermomechanical modeling and stuff. I picked up. I'm not parallel
Wow,
to it.
tungsten, you said.
So I picked up separately, and I was really fascinated because I was when I do the literature search, I was actually following your papers.
Oh, thank you very much.
So that was the real inspiration that I came here, because I was working. I had worked a lot in thermomechanical modeling,
Yes.
but and also DM methods and all those things.
Sure.
But recently I have also started to more look upon to CFD models as well, because
Right.
multiple physics is not able to properly captured in the FEM model. However, the FEM model is more suitable for macro scale
Yes.
modeling and all those purposes. But
Very
still,
good.
we are also having a earlier we used to do DED setup in our metallurgical department. There was one setup in our mechanical department. There is another setup. It used to be open means open environment. There was
Yeah.
not, so there was chances of oxidation and all those things.
Yeah.
But recently we got Optomac, so it's kind of hybrid system.
Sure.
So
DD with machining.
and
right.
this is not only this stuff. Actually, I am the only person working in this. In my lab, people are basically working in PhyB SEM, nanoscale printing, and
Yes.
and my professor is
Very
more
good.
controls guy. So
Yes. Yeah.
his field is entirely different. Means like underwater robotics and all those things. So it is entirely very diverse. So it is
Yeah, diverse. Yeah. Very
diverse thing.
good. Yeah, that's why. Or probably we can.
Hello, sir. Good morning.
Yes.
My
sure.
name is Misbah, and I'm PhD scholar from IIT Jodhpur, and I work in the field of metal additive manufacturing, basically in DED.
Right.
And my work currently is mostly on the experimental part, wherein I'm studying the composition control during additive manufacturing. So now
Composition control.
during additive. Actually,
Just
recently,
published one paper on the composition
recently I
change.
went through that paper with I think Professor Tohin Mukherjee. I studied that, and that's the
Right.
way I actually want to proceed in my work.
Right.
Like get into data with modeling,
Yeah.
computational modeling. So these things are what I plan to include in my work. So that was the basic force to join this workshop to know more about those things.
Good. Thank you very much for
Thank you.
coming. Sorry. Yeah. Yeah.
Myself, Rakesh Kumar. I am from IIT Ropar, and recently I have completed my PhD. I worked
Computer department or
mechanical department.
mechanical department. Yeah.
I completed my PhD in the biomaterials.
Biomaterial. Wow.
And
Okay.
currently I am working with process simulation, like multi-physics process simulation
Right.
for single track and multi-track, using both approaches like analytical and numerical. For
Sure.
numerical, I am using like COMSOL.
Which material you are looking at? Biomaterial, you said.
Titanium, TS6L forging.
Oh, okay. It's still metal. Yeah. Okay.
metal only.
I was thinking you're talking about tissue.
No, not metallic biomaterials.
Okay.
And we have used developed some model to predict the melt pool characteristics using thermal approaches and fluid flow, incorporating the Marangoni and recoil pressure.
Okay.
And apart from that, right now I've just started to process in the simulation itself multi-material to process multi-material during the process itself.
I'm interested in that multi-material.
I am also looking for a postdoc, so
Okay.
we can talk. Thank you.
Thank you.
So I am Ramesh Kumar from IIT Tirupati. I am working on
Tirupati.
electroplasma polishing of thin wall structures, which are
Oh,
3D printed. So that's why they are also
DT, thin wall structure
thin wall
using
structure.
LPBF or?
No, power bed fusion. We have EOS M290 mission.
Okay.
Powder bed. So whatever the printed structures having that lot of porosity, like surface roughness is very high.
Which
so we are
material you are?
steel 316.
Steel
So we are in
316.
a developing stage only. Recently we purchased, IIT Tirupati purchased that mission. So So there also we are applying the voltage 280 to 300 degree voltage in electroplasma polishing. Same pool will generate. So we want to study on that water plasma generation. So and a sustainable solution we are generating one solve solution. So
Very
whatever
good. Yeah, very good.
EOS M290. 290.
ASM.
Yeah,
Okay. Yes. We probably can continue after. Yeah.
Maybe from scientist we can.
Okay, sure.
We'll listen from him. He's a scientist.
Okay. I think we should have done this at the beginning.
Yeah, Professor. Professor, yeah, as I interacted with you, we are from Defense Metallurgical Research Laboratory,
Yes.
where we are working on this powder bed fusion and DAD for the past 5 years. So we have been printing specimens, components, and doing a lot of characterization, generating the data. Now we are just recently entering into the molding aspects of this LPVF, doing the single track, multi-track, multi-layer simulation. That's where I got stuck up with multi-layer simulation. But it's not easy to do. It's very
Sure.
complex, as you have been mentioning for a long time.
But now it's a lot easier than before. Yeah.
Yeah. So basically, our idea is to understand the melt pool dimensions and the temperature history, so that we can optimize the process parameters for the existing alloys, conventional alloys like maraging steel, Ti6-4, aluminum alloys, and also some novel alloys for futuristic materials and all. Let's say we are also looking at the optimization of parameters for the tungsten alloy.
Yes.
Tungsten.
That's also
Yes.
something I'm interested in.
Tungsten-based alloys.
High
So-
temperature refractory material.
Exactly. So we are looking at this molding and simulation on LPBF and DED also, basically for the optimization of process parameters, to get the metallurgical information and of course to derive the microstructure, to link it with the
Property.
microstructure and porosity related information from tomography,
Yes, sure.
and then predict properties.
Yes,
Thank you.
Sure. That's good.
Then we have a quick break. Before that, I have a few announcements here. So one could be on. So I hope you have corrected your spelling, if at all it is there. Then why? Because now we are going to send that printing. And one more thing, the attendance is also important for getting your certificate. You ensure that you are putting the signature daily, right? And there will be examination for the people who have opted for the credit earning. And if anybody wants to take up some audit also, it's not only for them. Anybody can take that exam, right? So we will make enough copies. If I remember correct, how many people? 18. 18 is compulsory. I'm taking for 18 people. Somebody wants to have, I will keep more copies here, so you can write the exam also, right? So basically
After the exam.
yeah, the examination will be on the Friday. That is between 12:30 to 1 o'clock. It's half an hour exam. 12:30 to 1 o'clock, right? So which is going to cover entire syllabus of Professor. Yeah. So basically, to be ready for that, right? Yeah, and then today's local visit. First, we are going to visit the.
I am at the National Institute of Technology, Varaku in India. So we have a participant here around, I think 60 plus people sitting here. So waiting for your presentation. So thank you very much. So Dr. Hong Hao Ge is actually, now he is also associate professor in the Zhejiang University of Technology. Am I right? In China. And then he going to be postdoctoral research associate at Queen Mary University of London. So yeah, he basically going to be my postdoc. And then today I invite him to give some how to say experience and also training on the simulation for defects and microstructure using sorry, I may need to repeat again. Okay, Hong Kao, I probably repeat again because we have some recording. I did record the team, I believe. Now, yeah. So let me introduce yourself. So you Hong Kao, Dr. Hong Kao, Associate Professor in Zhejiang University of Technology in China, and then he's going to be postdoctoral research associate at Queen Mary University of London. So today I invite him to give a talk on the simulation of defect and microstructure using CFD and Citroen software during melting certification from casting to additive manufacturing. So yeah, the floor is your Hong Kao, and yes, please. Can you speak now?
Yes. Let's continue. What is CFD? We know that CFD is short of computational fluid dynamics. It's a branch of fluid mechanics. It's a numerical method to solve and analyze problems involving fluid flow. And I think that key aspects of CFD include the four parts. First of all, I think is the types of fluid flow. CFD can simulate various types of fluid flow. For example, it's laminar flow and turbulent flow. And what's the difference between the two kinds of flow? I think is that it's the Reynolds number. For example, if the Reynolds number less than 2,000, I think it may be the laminar flow. And if the Reynolds number higher than 4,000, it may be the turbulent flow. Between 2,000 and 4,000, it's the liquid flow shows it is a transition state, I think that. And also, CFD can simulate the compressible flow and the incompressed flow. And the difference between these two kinds of flow, I think, is the density. If the density can change during the flow, such as like air gas, it must be the compressible flow. However, for our simulation, incompressible flow is very usual. For example, we take the melted metal into account, and other incompressible flow, such as water flow. Also, in CFD, the fluid domain is divided into small control volume. We call it cells or mass. And the governing equation of fluid dynamics, such as...
Do you move your slide? You are in the...
No.
Not yet.
Yes. Such as Navier-Stokes equation will be the main governing equation of fluid dynamics. And the third one is the numerical method. I think the CFD always uses the method like the finite volume method. We call it FVM to approximate solution to solve the governing equations. CFD is widely used in various industries, including aerospace, automotive, civil energy, and something like a chemical reaction set. It's used to optimize the design, configure performance related to fluid flow, and heat transfer and chemical reaction. And next is in this slide, I want to show that the common CFD tools. There are several CFD tools. Some of them are famous to us. For example, the edge printer and the console overform. They are widely used in different industries. Some of them are only used in their specific area. For example, the CFX are widely used in pumps and fans industry, and some CCM parts are always used in shipbuilding industry. In today's lecture, I want to introduce the anti-sprinter. And the anti-sprinter is widely used in industry. It's a world-leading computational fluid dynamics software. It's developed at the MIT in 1980, and commercialized by Sprint Incorporated in 1983. And Sprint has been widely adopted across the industry such as aerospace, automotive, energy, and chemical engineering. During 1990s, Sprint gained rapid popularity due to its robust physical modeling capability and ability to handle complex geometry. In 2006, it was acquired by ANSYS, becoming a key component of ANSYS product. Later, Sprint has cutting-edge technology like high-performance computing, cloud computing, and so on. By 2020, the integration of artificial intelligence, we call it AI, machine learning, and GPU acceleration has enhanced its simulation performance, enabling faster, smarter, and more accurate solutions for engineering challenges. Sprint continues to set the standard in CFD, driving innovation and delivering powerful tools to tackle complex problems in modern engineering and scientific research. Here I will show some simulation on Sprint Pro numerical calculated by Sprint. First of all is the common vertex speed. It's a periodic pattern of vertex following a series expected random numbers. And the second one is the mixed simulation of gas and liquid. In this case, the volume of fluid method is used to check the interface between liquid and gas. And the third one is about the fluid flow in pairs. The fluid can be used to investigate the fluid flow in the turbine machinery in parallel. It is important for understanding flow patterns in this case, and engineering can use this simulation result to design the pump or such like this component. And the fourth one is about the simulation air flow around the building. It's important for understanding window behavior and its impact on building. This CFD simulation analyzes how air flow over around between the buildings, providing insights into window patterns, size distribution, and potential turbulence flow. Additionally, aerodynamics always plays a vital role in the design and performance of aircraft by analyzing the force generated by airflow. Flow field simulation provides detailed insight into the behavior of air around the aircraft body, wing, surface. And for me, my research area is mostly focused on the additive manufacturing. This shows a typical additive manufacturing process. We call it laser powder bed fusion, LPF. These are typical of additive manufacturing that use a high powder laser to selectively melt powdered material layer by layer. And then we'll build a solid object from a digital 3D model. The key step is LPD process, including the powder layering, which means a thin layer of fine metal powder is spread on a filled platform. And then the laser will remelting the powder particles. And another layer of powder is spread on top of the previous one. The process repeated gives the object layer by layer until it is fully formed. After that, it typically undergoes further process such as heat treatment, surface finishing, or machinery to achieve final required property and dimensions. And here is our simulation about the metal pool evolution during LPVF. We can see the metal pool, we can investigate how the metal pool form, and it will move along the laser beam, and also in this case we can see the metal pool and the denser green growth during the metal pool solidification. And we can also see the metal segregation during the metal pool solidification. And another additive manufacturing process is laser direct energy depositing. When it uses a focused laser beam to metal and deposit material. Typically, the metal powder or the wine onto a substrate to create parts layer by layer. We call it LED. LED is sort of laser directly energy deposition. LED allows for the deposition of material directly onto an existing part or substrate. It's widely used to repair hot application and create a new component. Here is a video recorded by recorded by a camera. We can see the powder flow from the nozzle and how the particle rebounded by the metal pool, and how the particle into the metal pool and the melted. And based on the experiment, we also do some simulation about the metal to evolution during the LTED process. Here is temperature field evolution, also including the velocity, also including the metal flow in the metal pool. And this is microstructure evolution during the LTED process. Okay, let's back to the anti-influence. All about simulation cases are calculated by the anti-influence. And we know that if we want to make the universal simulation, we should get the May-Summerlin equations. In anti-influence, the May-Summerlin equation is presented here. And the computational domain is always divided into a series of control volumes. And the general conservation equation for mass, momentum, energy, and species are solved on each control volume. And for this Summerlin equations, there are 4 parts. First one is the unsteady term, and the second one is the convective term, and we call this one the diffusion term and the generation term. And if we want to investigate steady simulation, which means the physical phenomena is not changing with the time, and so the unsteady term will be omitted, will be neglected, and the Summerlin equation will become like this. And if our simulation is focused on a solid domain, which means there is no flow, fluid flow during our simulation, and the main Summerlin equation will become like this. We will neglect this one. And also, if we want to simulate like the steady state conducting in a solid domain, also in this simulation without consideration of any heat source, which means this one will be neglected, and the main Summerlin equation become like this. So, to us, if we want to make a simulation which should gather or should know the Summerlin equation firstly. And then if we do that, we can do the simulation in current software. There are 9 steps for make a speculator simulation. First of all, we should define the goals of our simulation. For example, if we want to do some research on our additive manufacturing, we should know what path For example, if we want to investigate the meta pool with the user's case focus on the focus on the meta pool or substrate or the sample. If we want to investigate the first data of shadow gap in the chamber, we should use a case focus on the shadow gap, and so different flows in the different simulation case or different simulation case. Also, we should prepare different math or geometry file or something. And after that, we should create a geometry and prepare the math file and then have the physical program, such as we select the models and also input the material properties, and also want to set the boundary conditions and so on. After that, we can start the calculation and get the result and at last we can review the computational results. Also, I think that the most important thing is update the model, because if we want to get a precise simulation result, we want to update the model maybe several times, maybe for a long time. Also, we want to compare the simulation results to our experimental results, and to check if the simulation results is in good agreement with our experimental results. And during the simulation, ANSYS front also provide important function we call it UDF. UDF is sort of user-defined function. It's a function written by user in language C, which can be dynamically linked with the front. And why we use UDF? It's because the front provides because the standard interface cannot simulate all user-specific needs. For example, we want to change the boundary conditions, such as if the boundary conditions varies with the temperature or some pressure and something else, or the standard interface cannot provide such function. So we want to write a function using the language C, and the printer will compile this code and list this function. And also, here in this slide, I want to show during the simulation where we can add or link the UDF. For example, later initialize use this macro to define the temperature or define the pressure before we start our simulation in the freezer domain. Also, within the loop, we can call for this adjust macro to modify the value in the simulation domain. Also, we can use soft to change the generation term which I mentioned in previous slide in the Darwin equation. And also we can update the property of material or the boundary conditions, and at the end we also can record the value of the simulation domain. And here I want to show is some example of defined macros. We always use this one, and this one is always be called for the simulation actually used to initialize the field variables. And also this one, the properties always used to update the material properties. And this one we can change the time status for simulations. And in this slide, it's another macro for geometry and time. And we can use this macro to gather the specific fields. We can gather the value stored in the specific volume. For example, using this macro, we can gather the cell volume, and this one we can gather the coordinate of cell centered in arrow axis. And these three ones are always related to the time. For this one, we can gather the actual time during our simulation. And this one, it will return the time step during our simulation. And this one is time step size. And in this slide is for the macros of physical parameters. And for example, density, pressure, and this one is mass fraction, and so on. And later I will show a simulation case from geometry, how to get our max file, and then how to set up the model, and get the results. And the case is about parabolic velocity net. In this case, there's a pump. The diameter is 2 millimeter, and the length is 10 millimeter. And we want to set the unit velocity is defined in this equation. And in the standard interface of front, we can only input a constant value. But in this case, the inside the inlet velocity is provided with the y coordinate. So we need to use the UDF to write this function. And we will use this macro and this macro. This one is used to obtain the center point of the inlet. And this one is after we calculate the value, and we will return the value to this macro. And this macro will set the value to the boundary of this simulation domain. And the first of all, we should prepare the code, and then we should compile the code and focus the code. Here is compile the code and focus the code. And after that, we can run the calculation and get the result. This result is the inlet velocity is 10 meter per second, and this simulation result is the inlet velocity is based on this equation. And I will show the whole process of this simulation case. And I created the slide first. And
yes, it will show the real fluent interface that you can look at how set up it. So this first case is simplest that you can understand how we set up this thing if you're not familiar with fluent software. Any of you here use Fluent for your research? So, ANSYS, Fluent ANSYS. No? Oh, you.
the geometry and make the max file.
Yeah, please note that it's not the Fluent case for additive yet. This is just the beginning. Probably, this is what you will see, right? I think.
And first we should create the geometry and the first point and the length of the tube is 10 millimeter, and the diameter is 2.
So create the geometry, I believe.
GIAN.
So I think the screen is dark, so we can't. Oh, okay, yeah. We saw the yellow
Yeah.
bar. Yes.
Yeah, after that we can create the face. In this software we created the geometry from pointer, line, face, and volume. Step
Face
by
and
step.
volume.
Yeah, and then we match the face, and after that we should define the boundary name of this geometry, and the inlet is one, the outlet is one, and the wall, top and the bottom. And after that we should define the simulation domain. We can choose this, if this simulation domain is further or further. In our case it is further. And after that we can export. Export the map. And then we copy the max bar as well. Copy the max bar and to the okay, we can fix this one.
So the first step is
we
to
have
create the mesh, and then you export that to import in the calculation. I mean, run folder, I believe.
yeah. And then we started the printer. Here is the interface, the starter interface. In our simulation is 3D. Here we can choose the dimension. Our simulation is 2D, so we choose the 2D. And here is the double precision. In printer, you can choose double precision, or it's the single precision. The difference between this type, I think, is the value of the value stored in 4 bytes or 8 bytes, I think. That's the only difference. And here we can choose if this simulation is serial or parent. If we choose this one, the simulation will run with number of process. And then here we can choose the serial. And then we copy to here. And then start. The version is a little older. Now the latest version of Frontier is 2023 or 2024. My version is 14, 10 years ago. And but the function is always similar. First we use max bar. This one. Here is the max bar. And because when we created the max bar, there is no unit in that software. Here we should change the unit. because in our simulation the unit in our simulation is millimeter, so we should change millimeter here, and so the filler is 10 millimeter long and 2 millimeter. The diameter is 2 millimeter. And yeah, in our simulation we are sizing it, so we just give it sizing it. And if you freezer flow varies is varies, we can choose the technique. Then in this case it's laminar and only one phase, so the multi-phase is closed. Also in this case there's no energy transfer, so the efficiency energy equation is closed. And the material is air. Also we can choose some other material. There is a further database in this software. For example, this one is water, liquid water. In our case it is air. And in this interface, we can change the material such as air or water liquid. In our simulation is air, and keep it as air. And then the most important is the boundary condition. In the inlet, we set the value is 10 meter diameter. Also, we can use this menu. In this menu, which means we can define the x direction velocity and y direction velocity. Here we can use the x 10. It's the same. Same to this function. And yes, and that's all. And we initialize and run it.
Okay. This is the velocity. Oh, sorry. This is the velocity result.
No, it's the result here.
Sure.
Yeah, this is velocity result, and we can see the pressure explosion, and we also can do some if we really want to know what's the velocity value along this direction, we can the inlet and the direction is here, and it's 10 meter per second.
Right.
Yeah. This is a single case, and also I will show how to use the UDF to change the inlet velocity with this function. And there's another case which I excuse.
Yeah, so this is just basic setup, and then if you want to demonstrate, yeah. So I think shall we move to the first cases and then we leave last two for the next session? So I think probably, or you want, or anyone want to see the how we implement the user-defined function? Yeah. Or you want to be okay? Can you show quickly? This is user-defined function, right? I think this is a code that we talk about. So write in C language. Yeah. Hong Pouch.
Yeah. In this case, we want to figure the inlet velocity. So we should write code. Easy code, and we should define the diameter is 2 millimeter, and define a further value. And this area will be used to store the coordinate around the y direction.
Yes.
And yes, and we will group the boundary of inlet and get the specific field, and then get the coordinate of the field, and store in this area, and this one is one coordinate, and we already know that x x is here. The arrow always from 0 first, and then we use this function to calculate the inlet velocity, and then back to the boundary condition, and assign the velocity. And here I will show how to compile this code and link to the point. Here is the code, and start the point firstly, and use the math, and change the limit.
Yeah, repeat the same, but now we're not going to define using the constant velocity like before. But later we will impose the boundary condition with the function of y. Yes, please.
The same, and you just and we should compile the code, and add the code and build, and then load, and you can we can see the x velocity is loaded in our software, and then we can see there is velocity here. We can choose this one, and it means the code is dictated by the software, and then we click OK, and inside, and then on. And we can check the result. What's the difference between these two images? And GIAN has duality and in terms of it's different to our previous simulation, which means the inlet value has been changed by the code.
Yes,
this
it's
code.
changed from the panda to parabolic velocity profile.
Here is different result between these two simulation cases.
Very good.
Okay, then let's continue.
Yeah, shall we pan like this? So we have 3 cases. So you will show from next half an hour on the first cases, and then we show the next 2 in the next session. Is that okay? Is that your plan?
Any questions?
Any questions so far?
Yes. Or I will continue our
Yes,
lecture.
please. Yes, please. Yeah.
Okay. Next one, I want to introduce 3 complex simulation cases. First one is about the solidification of large-scale ingot. Large-scale ingot always used to fabricate the rotor component, and the rotor component always it is an important part of power plant or steam turbine, and the ingot always will be fabricated by pouring metal into a model and solidified. Because the ingot is too big, the weight of the ingot, I think, hits over 10 tons, about 10,000 kilograms. In our simulation, I will present 55 tons. And after the solidification of the ingot will take 1 week or more than 1 week time to solidify after the liquid poured into the mold. After that, the ingot will be forged and machinery. Finally, will be assembled as a rotor component. And because the ingot should take a lot of time to solidify, the liquid in the mold will flow from here to there under the thermal-fluid buoyancy force. So after the solidification, the ingot always will be cut, and we can find micro segregation in the center of the ingot. the macro fabrication is an even element, uneven element distribution on the macro scale of ingot. It's undesired effect of the solidification, and it's difficult to eliminate by the downstream process, such as the forging, heat treatment. It's difficult to it's difficult to eliminate it. As all we know that the typical metal segregation in the center of the ingot include the top positive segregation and bottom cone-shaped negative segregation, and also in the center of ingot will appear V-shaped channel segregation, and also A-shaped channel segregation in this area. And our purpose is to build a numerical model to reproduce all kinds of this macro segregation. And during the ingot solidification, there are several physical phenomena here, such as shrinkage, because the density of liquid and solid states are different. So, as the solidification progress, the liquid will be the air will be sucked from the top of the ingot, and finally the shrinkage cavity is formed in the top of the ingot. Meanwhile, the nucleation are always occur in the center of the metal, and with the growth of the grain, the grain will move from top area to the bottom area, and finally accumulate in the bottom of the ingot. Additionally, the columnar always grows against the border wall and grow into the ingot center. During the growth of the columnar grain, they have the ability to catch the actual grain. And if the tip area of the columnar is full of actual grain, they will block the growth of columnar grain. And finally, there's a PET room appear in the bottom of the ingot. PET means columnar to equax transition. Also, in our simulation, the columnar face is summed as a cylinder, and the equiaxial grains are summed as ball or in our face, crude. This is our main conservation equations. We can see that the mass transfer only occurs in the liquid phase, equilibrium and columnar phase. And the transfer transfer are existing between all these four phases. Also, the momentum of in our simulation, the columnar is set as stationary. So the momentum compensation for columnar phase is missing. And here is the interaction between four phases. The mass and species transfer only occur from equator to equiaxial and equator to columnar grain. But the momentum and energy transfer are carried in all four phases. Here is the flow chart of the solution for easing of computation, including the change equation such as this one, and the software equation, and the most important value is the mass transfer rate during the simulation. in our simulation case, we use the user-defined adjustment micro to calculate the mass transfer rate firstly, and based on this rate, we can calculate the momentum transfer rate and energy transfer rate. Translate. And also we use the user-defined property to update the viscosity of solid phase. Here is the initial and boundary condition for our simulation. The ingot is about 4 meters high and 1.5 meter wide. It's about 55 tons, and here is the initial species fraction, and the initial temperature, and this is the boundary condition of this ingot.
And this is the steel, this is the copper steel, right?
Here is the carbon steel.
Right.
We only consider two elements in this simulation case. Actually, I think it's several, maybe
yes.
four.
May I add a little bit? So this is the large ingot for the copper steel here, that we want to understand the fluid flow during the casting, because this fluid flow is origin of the micro. I think now it's macro segregation. So as you may imagine, the segregation is quite detrimental to the part. So what he want to do now, he will simulate the thermal solutal fluid flow. That means you get some dendritic growth, fluid flow, and also as well as segregation profile. So what is the concentration, or what is the element that you are looking at? The distribution of the carbon, right? That's what.
Yes.
Right. Okay. Sure. So So that is the aim of this one, in order to identify defect and try to minimize as much as possible. So thinking of, and this one is has its real use actually for industry. So yeah, sorry, yeah, please go ahead.
Okay. And here is our simulation result. And this figure shows the evolution of macrocyclic and this one is liquid phase practice during the qualification. And this one is founder phase distributed during the qualification. And this one is liquid extra green.
Okay, so this one, yeah, this is not Serra Automata. It's based on the kind of indexes that you want to identify the morphology of the grain. So this is no real equax or columnar simulation, because this is 15 tons of steel. It's not impossible. So again, you need to understand. So they use the kind of variable to identify this columnar or equax, and then that is the location you would expect it to see. Imagine this is 1.5 meter long and then about, is that 4 meter height, right? So it's a very large.
Yeah, 4 meter.
Yeah, so it's a very large part. But again, this to give you some idea what we do, why so matter. Segregation later you will see in the next cases in additive. But yeah, yes, please, sorry, please.
Okay, from the growth from the wall into the center, and it takes the grain, nuclear, and the feed down, and accumulated in the bottom of the ingot. And we know the carbon will be rejected in the liquid phase as the solidification progressing. So the concentration of carbon in liquid phase are increased during the solidification, and finally in the top of the area, the concentration of carbon is very high. Finally forming a positive macrosegregation. Yeah. Also, during the solidification, the synthesis cavity is forming in the top of the ingot. And based on this simulation result, we use this to compare with experimental results. And here is this one is the simulation result, and this one is experimental result. And we can see that both of them have the positive segregation in the top of the area, and there is a cone of the negative segregation in the bottom of the ingot. Here is sample print of real ingot. Both of the simulation results are in good agreement with the experimental results. It indicates that our model is relatively reliable. And then I will show how to build such complex model to reproduce this microsegregation during the large scale ingot solidification. And then I will show the similarities. Here is I think it's this one. yeah, this one is the code. Very complex code. It's about 2,000 lines in this case.
So now it's not 10 line like previously. So we need to code up the equation that you showed before, 4 set of equation in this one, and then try to solve it. It's the same principle applied for additive as well, but probably additive is longer because you have complex of the boundary of, yeah. So just because I just look at the time, it's okay if you finish these cases and then we continue 2 cases in the next session. I think that would be good.
Yeah. And we should load A.
So how long does it take to calculate this part actually? I don't think it's going to be finished in
I think at least 1 week.
1 week. So it's 1 week of calculation. So I don't think we're going to make it. Yeah, but just show you. And I know if you are in the metallurgy field, you know how important of this profile is. And not many people around the world can do this, I believe. Yeah. It's quite complex geometry, and how accurate is another thing.
This is a proper positive segregation, and this one is a quantum negative segregation. And here is a code. And in this code,
easy code
I
is one.
Yeah, this is the code. I think it's most important value is this one. We want to get the mass transfer rate firstly, and based on this value, and we can calculate the species transfer and calculate the energy transfer. Energy transfer is here, and also this one is the thermal buoyancy.
Sure.
Yeah, and this function is used to calculate the number of nucleations.
So when you say number of nucleation, can I ask what is your definition, or what is your given condition for nucleation here? How did you define that?
I think it's based on the, I should share the first.
It's actually just a normal distribution of the nuclei on the wall of the ingot, or is that something like that, right? I believe.
Yeah.
Okay. So you take that distribution from experiment, or what did you do? How did you define that? I think this is probably the question people here may want to know. Yeah.
This value, this result.
Yeah. Yes. Yeah.
The experimental result is provided by another group.
And understand.
Yeah, because if we want to fabricate such a large scale ingot,
yes,
it will take a lot. It will cost a lot of money.
Okay. So what is the assumption for that? Would that be you can you remember that? Is that for example, if this is steel copper copper steel, right? So you're talking
Yeah.
about 30 to 50 micron average grain size that you as initial condition, or what is that actually? So you just
Yeah.
randomly assign the seed of the nuclei at the wall of the ingot. Is that what you do?
Mm. Yeah.
Okay.
Also we neglected the pooling process during the simulation, and we assign the temperature at this value, and then begin to solidify.
Okay.
Mm.
Yeah, but anyway, this is just artificial, I would say, boundary for degradation, because it's not actually solve the density growth directly. You see this one, it just treat it as a set of phases that contain some property for that. That's what I understand, right? This what you, yeah, I think, okay, yeah, hopefully it's clarified. So I think probably this is a time for question before we finish this session. So we will continue the two cases, and then we will show more about density growth and the 3D printing next one. So what, do you have any question here for him? I can speak here. Please, I know you want to ask something? And anyone want to ask anything so far? So the one who used Fluent, I think Kishore is not here, I think. Oh, okay. You want to ask something? Are you trying to do simulation for additive as well? Have you experienced in the UDF?
Oh.
I'm asking the audience here.
No,
I know you, so experience. Yeah.
Actually, I'm working on CFD, sir,
Okay.
and lattice structures, fluid flow analysis.
Okay.
That's the.
Yeah, I mean there is an audience here. He doing some lattice structure, and then
Fluid
they
flow
try
analysis.
to use in Fluent. They try to understand the fluid flow allow that lattice structure. Is that something?
For
you
finding
have
of the
done
permeabilities, sir.
Have you done any?
Yeah, I
computation?
had done, sir.
Okay.
So that's why I want to discuss with you regarding
sure.
journey,
I
sir, return journey.
We can do something, yeah.
Yeah.
But that means you didn't print the structure. You just assume a structure and then you see the fluid flow in this structure. Okay.
Yes.
It would be interesting what happened if this is actually an implant, for example. It would be an implant, right? And then you print it, and then with some surface roughness, this may be different, I believe, with the smooth surface that you have.
The last work was it take 45 days, sir, to me for last work in CFD simulation. 45 days.
45 days. 45 days, yes, I think it's too long.
Yes, sir.
I think Hong Hao.
Number of submits are more, sir.
Allowing within 1 week. But
number of
anyway,
submits
we can exchange some idea.
Yes, sir.
Yeah. Any other question before we finish this session? I think next one would be more exciting. And if you want to do more segregation, density growth, cellular growth, and then 3D printing, next one we will have a very exciting section. Say again? Which one? Yeah, that's isotropic material property. Yes. Yeah, for this one. Actually, is that correct, Hong Hao? We assume isotropic material property. So, but having said that, some casting cases for nickel superalloy, as far as I'm aware, they can do some anisotropy property as well. But that is more another layer of complication. We didn't show it here, but definitely we will can discuss further on that. But because we can't show everything, so just give you some idea. So this density growth may be useful for the grain growth, and then especially we're going to have one paper with Inconel 718. So predict the lava space, which is the PCD, right, for going to show something like that here, or probably just mention briefly, right? Not completely. In the second cases, I believe. Hello, Hong Kong.
Okay.
Yes, yes. If not any question, I think we can come back in about hour. Hong Kong, I will. Please,
I know.
yeah, please connect in about 1 hour, and then we continue for case 2 and 3. Thank you very much.
Okay.
Thank you, and see you.
Thank you.
See you. Bye bye.
See you later.
Bye bye. Bye.
Bye.
So the lunch is arranged as usual, but there is a one special some non-veg item is also arranged. Somebody is non-veg vegetarians, so you can enjoy it. Yeah, thank you. Thank you for the. So we'll assemble back at 2 o'clock, and 2 to 3:30, and 3:30 we are going to local trip. వెజిటేరియన్స్ ఉంటుంది లేదు
speak something, Hong Hao? Hello?
Yeah. Hello, Professor. Can you hear me?
Yeah. Not sure. Left. Light.
No, ఇది ఆడియో జాక్.
Yeah, that's what I think.
Here.
Can you speak again? Oh.
Yes, Professor. May I start now or a little later?
Yes.
అక్కడే ఉంది.
Okay. Can you speak?
Yes.
Hello?
Let's start.
Yeah, you can read the. Thank you very much.
Okay.
We were testing the
Okay.
sound. Yeah.
Oh, introduction of IC front software.
Yes.
Is that okay?
Is that okay? He's speaking.
Simulation on the solidification of large scale records.
Can you speak again or play something?
Introduction of ANSYS front software. Simulation case 1.
ఎక్కడ పైన ఉందా? అది ఎక్కడుంటే అక్కడ పెట్టు.
Is that okay? Yeah. Put.
Simulation on the solidification.
Okay, that's good. Okay, good.
Okay.
Yeah. So, shall we start? Do you think? Or we Yeah. So I think because we have time restriction, so we will start now. Hong Kao. Yeah. Please continue your presentation. Yes.
Okay, thank you,
Thank you very
Professor. Hello, everyone. I will continue my presentation now, and I will show the next simulation case. It's about a simulation on the dendritic grain growth. In this case, we will consider the magnetic field assisted solidification. Magnetic field assisted solidification is important for many process technologies, such as directional solidification. Here is a schematic description of directional solidification. During the solidification, the external magnetic field affects the microstructure by influencing the matter flow, heat transfer, and solute transport process. The directional solidification experiment inside Bridgman furnace. This is a Bridgman furnace, and the thermal gradient was imposed by heating element. This one is the heating element, and the cooling system in the bottom of the sample. Both of the heating element and the cooling system to keep the sample with a constant thermal gradient during the whole experiment. And also, the K-type thermocouples were used to monitor the temperature and adjust the temperature. And this one is the final microstructure characteristics after the metal solidifier. And because of the effect of the magnetic field applying on the metal liquid when it's solidified. So there are several physical phenomena occur in this solidification process. And it was as we know that the application of a standard magnetic field will inhibit the metal flow due to the Hartmann effect. However, in our simulation, in this case, the application of standard magnetic fields during the solidification has also been found to drive the metal pole flow through the dendrite. The effect we call it is thermoelectromagnetic force, which always generated by the feedback effect. And what's the feedback effect? We know that like the thermocouples, the temperature, we know that the metal with a different temperature and with different temperature and they has different feedback coefficient. And so in the because solid and liquid has a different temperature distribution, and also their feedback coefficients are different. So in the surface of solid and liquid interface, there will be a thermoelectric current occur. Yeah. So under this thermoelectric current and the magnetic field, the liquid will flow under the Lorentz force. Yeah. So
I think just to set the scene for the people participant here for this problem, I think as you know, we have some research in additive manufacturing with we call field assisted. So we use electromagnetic field as well doing the deposition of the additive. So I think this may be relevant or applicable to that context, how the dendritic behavior during that, I mean, when we combine. So that means Hong Kao going to explain to us, we need to add another equation on top of this one to take into account the magnetic field. Yes, please.
Yeah.
Thank you.
Okay. And in our simulation, the main conservation equation are presented in this slide, and here system is the thermoelectromagnetic force, and in this case, only two phases are taken into account: the liquid phase and solid phase. The solid phase is stationary, which means the velocity of the which means the velocity is zero, and the liquid phase are movements, and the velocity is solved by this equation, and this one is the thermal solute buoyancy force during the solidification, which will drive the liquid flow in the simulation domain. And also, this case is built based on cellular automata method covered with multiple phase approach. And here I want to introduce the cellular automata approach. The cubic grid cell was used in current model. We know that the cellular automata method, before we use this approach, we want to define the state of the cell. And in our simulation, we define 3 states of cell. The first one is liquid and interface, and the third one is solid state. And the solid state cell have a solid phase fraction of unity. Means the phase fraction is 1, while liquid cells is a solid phase fraction of 0. And the liquid flow only occur in liquid cells and interface cells. And the interface cell has the ability to catch the liquid cells, and with the solidification progress, the interface will change to the solid cells. Here is the flow chart of the different cells. They will change their state by this flow chart. And also, I want to introduce is the that if this the blue one is the interface cell, there will be a square appear in this cell during the solidification of the interface cell. The square will grow bigger when they touch the neighbor cells. Usually the neighbor cells is the liquid cells, and the interface will catch the neighbor cell as an interface too. And meanwhile, there's a square appear too. During the solidification, these squares will grow up and catch the neighbor cells. Finally, the interface cells lose the capture ability when it changes to a solid cell, as the state and the solid volume fraction updated. The progress of the melting solidification is predicted, which means we use this progress to simulate the dendritic grains grow. And in this simulation, we will use this macros. And here is the initial and the boundary condition for our simulation. There are 3 nucleus in the bottom of the bottom of the simulation domain, and also we will apply a thermal gradient with 6,000 K per meter. And the left wall and the right wall is pressure out. And this is the initial temperature and the cooling rate of this simulation. And here is the evolution of dendritic growth. And we can find that this case is without a magnetic field. This one is under magnetic field. And the main difference is that the max velocity of liquid in this case is larger than without a magnetic field. It's about 0.0017 meter per second. It's much larger than this case. And also we found that here we can see the symmetrical characteristic of secondary dendrite. And in this case, it's symmetrical. It changes the characteristic of the grain.
Yeah, so I have few questions here, Hong Hao. On the first three figure on the left hand side, this is the without magnetic field, right? Or with
yes.
The left hand side, this is no magnetic field, and the right hand side has magnetic field. Is that right?
Yes. Yes.
And this is one question. The second one is actually, what is the material system we are looking at now?
This is aluminum and copper.
Aluminum copper alloy. So aluminum.
Yeah, copper. Aluminum copper alloy. Yeah.
Yeah, and then you are looking at the segregation profile of the copper. Is that correct?
Yes.
Okay.
Copper is a species.
Okay.
Yeah.
Yeah. Thank you.
And we also see the detailed interface appeared in this case on the magnetic field. Also, the experimental results also show the similar results we can see in this picture. And then I will show how to build this simulation case use the front analysis front.
Yes,
and
sure. So I believe you also will show as well the code that used or customized for these cases as well, right? That you need to compile to set up this, right?
Yeah.
That's good. So this is different from the previous cases in the sense that we implement another computational approach, which is say CA or cellular automata, combined with those four equations that we use. Is that correct? That is the differences.
Yes.
Okay, sure.
And in this case, we use the Euler multi-phase.
Yeah, multi-phase Eulerian framework. That's we use here.
Yeah, and we will open the energy equation, and here is the material, and also the property of material are written by the UDF.
So this is
And
a thermophysical property for each phases, right? That you define for the system. So we have about 7 phases, I see previously. So you have aluminum, liquid, solid, something like that, and then copper, liquid, solid, and then what? Yeah, that's right.
we should create a ISO interface and
What we are looking now is a temperature history. Sorry, temperature distribution, temperature field, I think, right?
here is the dendrite, and then they will grow up and then as the solidification progress, they will grow up again, and like that. And here is the code. Code, I think, is in the most important part is.
Okay, sure.
In this part, we apply this force. We call it thermoelectromagnetic force in here, and we use the defined sources macro to add the force. The force is in 3 directions. Here is the x direction and y direction and z direction. Z direction. Also, we consider the thermal buoyancy, thermal through buoyancy. This one is thermal convection, and this one is through convection. And our results also can see the
So this one, I have another question. You actually simulating the alloy system, aluminum copper. How you take into account the segregation then? In terms of you will need to have aluminum and copper separately, and then you do some calculation about the thermodynamic kind of behavior, right? Did you incorporate this here or no? It's just
sorry. What's the question?
Yeah, did you actually consider thermodynamic for aluminum copper system here?
It's a binary.
Okay, so it's actually in your code as well?
Yeah, it's a binary alloy.
Okay.
Okay. Yeah, aluminum and copper. I think.
This is through material property, right?
Yeah, this part is material property, and we can define the density, specific heat, and something else.
So this material property calculated from the thermodynamic software, I believe, as a temperature-dependent property. Is that right?
Yes.
So basically, you calculate a phase diagram some way, somehow, and then import that into this model, and then kicks out everything.
Yeah.
Is that correct?
Yes, I will always use the GMAT Pro. This software. Yes.
So anyway, this is actually a bit weakly coupled approach. Do you think we can do strong couple? Let's say let the software communicate with each other and then feedback the kinetics because this maybe actually have kinetics. Is that how can we take into account the kinetic into this problem actually? Sorry for asking. Is that relevant question? I believe to, yeah. I'm not going to examine him, but just asking the question for the benefit of everyone. I believe it's useful. Yeah, sorry for asking too many, but I think this is important information.
Yes, I think so.
You will appreciate that this is not simple calculation. It needs to communicate with many software, many coding, programming. Even you have the, I think not too cheap software packages. Yeah, you still need to work a lot. But the thing is you have developer to help you to, debugging the code if you pay more to get a new version. But our job is to worry about equation. Yeah, but if you do open source, probably everything depends on you, how good or bad like me at the beginning. So it's run very slow because we don't have people to help on other aspects. But anyway, yeah. So you want to show GMAT Pro what you did for the aluminum copper system, or what? I think I saw you open the GMAT Pro. What do you want to say?
Yeah, and in GIAN Pro we can input the concentration of the element, and then we can run. We always use the solidification part, and then we'll run the GIAN Pro and get the density, and we can.
That means this actually depend on the available database for this material system. I think this is probably it depends on how you buy this software, which company you select actually to get better. This also come with cost, I think. Yeah, but currently we use this software GMAT Pro. But some application for me, we use other thermodynamic software packages as well. So as you know, you will expect different database.
Yes, and the software can provide the density.
But that is assumption made by
liquid viscosity and thermal conductivity.
So this is all the thermal physical property temperature dependent, right?
Yeah. Yes.
Sure.
Yeah.
So, but if the temperature go over, let's say in this graph, go over 1000 Kelvin, so you will need to be, extrapolate or approximate it, right? To be, that is also another point for the thermal physical property as well.
Yeah, and close the.
Yeah. So let's say you export the table like the graph. It will be probably tabulated or function whatsoever, and then you call the temperature when needed at the centroid of the temperature field, so that you don't need to worry about. It's just about the value of temperature and assign the property of that. I think that is usually standard approach we do. Yeah. Let the computer working on it. Yeah. Anyway, thank you very much. So what you want to show next, please? Hong Hao, please continue if you.
Okay, I will close this one, and we'll to the next simulation case. And next simulation case, I will introduce the additive manufacturing. And the first one is the LDD, which I has measured in previous slide. LDD is short of laser directed energy deposition. That use focused laser beam to metal and deposit material. Typically, it's a particle. Sometimes we will use a wire. And in this slide, this is the LDD process, and we use a high-speed camera to record the deposition. And we can see that the powder particle flow from the nozzle, and some particles rebound back, and some particles flow into the metal pool and remelted. And also some particles into the metal pool and flow around the liquid. And the LDD process always deposition on a material directly onto an existing part of substrate. Here is the substrate. And so it's very important to introduce it's very important to investigate the flow, heat, and mass transfer in the metal pool. And we also build several simulation cases to investigate the physical phenomena during the LDD. Here is the microscopic equations, and include mass conservation equation, and momentum conservation, and energy conservation equations. These two simulation cases show the temperature distribution, and also the metal pool evolutions. In this case, we present the dendrite growth during the metal pool solidification. Also, we can obtain the result of microstructure characteristics. And and then in our simulation, in our simulation, we have built two two cases. Between these cases, we want to use the temperature data to link each other. And first, we acquire the temperature from the microscale multiple model, and then we use this temperature data. We transfer this temperature data to the micro scale model. For the micro scale model, we also use the cellular automata method. And in this simulation case, the grain structure, solute segregation, and the dendrite structure are all will be considered. And here is the flow chart for the temperature transfer from this model to a CA coupling model. And also we do some experimental result. Do some experimental and comparison of the cross-sectional morphology of the metal pool from the experimental and our simulation results. The material used in this experiment and simulation is a kind of super alloying. And this is the parameter for the experimental and simulation.
So
yeah,
this is super alloy. This is super.
Yeah.
Right. And what is the super alloy here? Is that 718?
Yeah, Inconel 718.
Okay, this is Inconel 718.
Yeah, and here is the microscopic simulation results. The evolution of temperature distribution and the metal pool are presented in these figures. And after that, the temperature will be outputted when the metal pool is stable, such as for this time, and the temperature will outputted to the micro scale simulation case. And the temperature will be linear interpolated from the microscopic temperature fields to the micro temperature fields. And later I will show the code how to make this linear interpolations.
Yeah, so basically when you want to basically link from the macroscopic temperature field from oily multiphase solver, you need to approximate, you need to export this temperature field to the cell automata, right? Situation.
Yes.
But it's still, there is a, I would say, probably we say problem, because there's a mismatch between the match in the temperature field, which is normally larger than the match, because you are capturing the dendritics scale. So we are now, this is another numerical treatment that we need some way somehow to interpolate the temperature in between, because let's say your mesh is 1 millimeter and you want to do 1 micron, something like that. So that means you need to interpolate the temperature in between. Yeah. So yeah, that's what it's doing. Yeah. Thank you. Yes.
And here is the simulation results. We can see that this part is the substrate microstructure characteristics, and we can see some grains has epitaxial growth, and also some equiaxial grain nucleation here, and the columnar and the equiaxial similar the columnar grain and the equiaxial grains will competitive growth. Finally, in the top of the metal, in the top of the metal pool, the columnar to the equiaxial transition is found. And the primary, the PDS is the primary dendrite arm space and grain structure for simulation results and experimental results are compared with each other. And the results shows they are in good agreement. And also we compared the experimental results in this figure, which is the EVSD result.
So you are looking at the dendritic growth on the top left hand side here, and then looking at the segregation profile of niobium, right? This niobium is actually the important segregation profile for lava space, right? And then you're looking at for different location in the mel pool. I believe that is in the mel pool, right? This 10 for the bottom. This is only one deposition, one layer.
One layer.
Only
That's
one
layer.
So okay, yes, yeah. So this is only one layer. You see some differences here, and then you compare this result with the EDX measurement. Is that right?
Yes, this is the EVSD measurement.
And this is the result on the bottom left here that you see simulated and then experiment. Okay, thank you. So basically the qualitative comparison, not exactly match, but it's in the same trend, I believe. Yeah, sure, that's good. So yes, please.
And then I will show the simulation cases, both of macroscopic and microscopic.
Sure, please, please do that.
Okay. And we click the place.
So this is a macroscopic model that you're talking about. This is thermal soluble fluid flow, right?
Yes. Here is the temperature distribution result, and I will add the velocity of liquid flow is here. And we can see that the liquid flow from the center to the side of the metal pool because of the magnetic force. And here this one is and this is hold for this case.
Okay, so this is a macro, right? Or this is both of them combined?
And if after this simulation, we output the temperature history to the macro microscopic simulation is here. This one.
This is what? This is the cell automata, right? This is a micro.
Yes, cell automata and the linear, and here is the temperature from the
previous
model.
Temperature.
Temperature from the macro, and we will do some linear interpolation. Yes, interpolation, and get the according the coordinate and the time, and we will calculate the temperature. Such as
this is the temperature field for every time step, is that right?
Yes, every time step.
Consider.
But
so
we use the coordinator and flow time to calculate the current time in the specific cell.
Okay. And this actually, yes. So you take about a quarter or 1/4 or half of the melt pool, is that right? You simulate half of it.
Yes, only half.
Only half. So basically, he saved some result each for particular time step to show us. Now I think load some result. So you may appreciate that this is a huge data that generated from this kind of this kind of simulation. But that
the
means
mesh
the data
size
processing is something you also need to code up to basically get this data to be similar to run the video as well, I believe, right? There's another layer of coding. Yeah. Only 2D.
Yes.
But we will show next
slide only
3D. But you will see here how surprising the dendrite actually break up and then form the equax grain at the top. This is how the transition from columnar to equax grains happen. So this simulation gives very detailed insight what happened. Yes.
Yes, here is the micro segregation during the multiple solidification. Yeah, we can see the species, the elements are enriched in the liquid area during the solidification, like here. And
yeah, this is automatically coming out from simulation. We didn't assign anything. Just let it go. Yeah, but under the representative temperature history, this may behave differently. Yeah. So that's what it is. And again, just to remind you, this is aluminum copper. This may be different from nickel, I believe. Anyway, thank you very much. I think I just watched the time. I think it's probably interesting to briefly explain the last cases now with the powder-based fusion additive that we are working on at the moment. Yeah, I mean, he just want to show how detailed you can get with the niobium segregation profile. To me, it looks like a micrograph that you can take from PDS or yes, yeah. So that's what the level of modeling we're interested in. We like to do in this kind of simulation because these simulations length scale that we are looking at provide extra information from normal simulation like heat. So you won't be able to measure this easily. I mean, doing printing I'm sure, right? So not yet, no one measure the microstructure evolution during 3D printing yet, as far as I know, yeah. So this is an opportunity that we can get further, especially if the part is quite complicated, but not too complicated. We can replicate what happened as well. I mean, again, yeah. Thank you very much, Hokao. I think, shall we move to the last one with the powder-based fusion, in situ alloying? Yeah. Yes, please.
Okay.
Yes. Do you assume the black diffusion of the solute, back diffusion, right?
Yes.
Did you? Okay, yes, he did. So you can find more information. I think it's not published yet, right? This the one you show. We are going to publish this one, I believe. The work you just show on the dendritic growth there is not published yet. Is that right?
Yes.
Okay, so we can share with you later when once published. But there's some other paper talking about niobium segregation profile as well. It's not just us. I think, yeah. But anyway, this is the powder-based fusion now.
Okay.
Yes.
Here is a laser powder bed fusion. We call it LPBF. It's another typical additive manufacturing process. And that use a high powder laser and selectively melt powdered material layer by layer. Nowadays, scientists use synchrotron X-ray to observe the physical phenomena during the LPBF process. Here is the simple result. And X-ray will penetrate the sample, and there is a monitor behind the sample, and will receive the signal. Different materials have different capability to absorb the X-ray intensity, and finally, the monitor receive different signal to observe the metal evolution. In this result, we can find that due to the laser shock, some particles are flow away, and some particles are remelted and become melted liquid, and the melt pool is forming gradually. And because of the surface tension, the liquid always looks like a ball, I think. And then we want to do some simulation about LPBF. Firstly, we should build the conservation equations. In this simulations, multi-phase model was considered, including the liquid phase and the air. The volume of fluid method was used to check the interface between these two phases. And for this equation is about the energy conservation. This one is the laser heat energy, and these three terms is about the heat loss during the progress And this one is convection, and this one is radiation, and this one is evaporation. And also, we use the momentum conservation equation to obtain the velocity of liquid. Here, the liquid is metal, and in this equation, this one is the density term, and this one is the surface tension term, and the magnetic force and the coin pressure, which arise from the evaporations. And this is the physical parameter for our simulation, including the laser path, scan speed, and laser thickness, and so on. And this is the initial and the boundary conditions for this simulation. Here is the result of evolution of metal pool and the temperature field. We can use the cross section to describe the evolution later. And this one is the volume fraction of liquid, and this is the temperature distribution. And the temperature, this one, and multiple and the velocity distribution are presented in these two pictures. The solid metal particles were gradually heated by the laser to form a multiple, and the shape of the multiple was basically stable after a period of time. Due to the extremely high laser energy density, and here, like here, a distinct concave shape is forming in this area. If the laser energy large enough, the keyhole will form, I think. As the laser spot moves, the liquid metal gradually cooled and solidified to form a solidified check, like this area. And sometimes there's okay, and also I will show the simulation result by the Access Front software.
This is the pure element, right? The material you are looking at here is a single material.
Yes.
Okay, sure. Yeah, what is can you comment on the computational resources used for this simulation? match. Oh, element. I think there are two models, right? The first one is the macroscopic, right? Oh, in this case, you don't do any cell automata. So this is a hexagonal match. Is that correct? Or
Yes.
Yeah, it's hex match.
Hex match.
Hex match, yeah. So, but cell automata is also hex match as well. But some CFD, it will be tetragonal, which is, again, depends. But you can use hex match in crystal plasticity as well. But
Powder, in order to match the powder
Mm.
so fixing the hexahedral mesh system within the powder particles, it must be difficult. Is it because it
Good
won't?
question. So it will be about approximately about 5 elements across minimum. And because this is interface capturing, because what we see, we will, I think he didn't mention at the beginning, it will be the whole calculation domain, and then we identify some boundary to be a phases for metal, someone is for the air. So during that interface definition, we will class across the hex match. It's not because some element will be, because it's volume of fluid, it's strict volume, so it will be, can contain both phases at the same time. So it doesn't matter, it's a moving interface problem, yeah. So it's not fixed interface.
So
you see what I mean, right? Because in one element you can have both phases existing at the same time.
Correct, understand.
Its volume is fixed.
Volume fluid.
Yeah, volume. Finite volume, yeah. Okay, next please.
And and for this case, this one is manganese force, and this is coin pressure force in this simulation case, and also they has 3 directional x, y, and z, and we can see that. And and in this case, the volume of fluid method is used to check the interface between liquid and the sample.
Right.
And yes, and also the liquid flow is some the laminar flow.
It's laminar flow. Okay, good.
Yes. Also, here.
What is the mesh size here?
Mesh size is about, let me check. 4 micrometer.
4 micron. Not too small. I mean, I see. Yeah, probably in CA you may need smaller mesh size, I think.
Yes.
I mean, we did some CA, so it will be probably 1 micron for CA, right?
CA, I think, is 1 micrometer or smaller than.
64 times lower, so more very high resolution. But anyway, it's about right. It's about in order to 5 to 10. It depends on how big your domain is. But at the moment, for the conventional CFD like this, we not tend to apply adaptive match because this would be so problematic. But now people try to use this for the very extremely complicated detailed dynamics that they want to know. Yeah, but that's it. Leave it for another matter. That's related to more computational technique. Yeah.
Do we need discretization scheme for each and in order, do we need to change the discretization scheme for each of the term in momentum equation in order to get proper, more realization of the physics? Which I just want to know. Discretization scheme like Gaussian, linear, all those things. Forward.
At the moment, it's not changing. Well,
Okay.
I don't understand your question actually.
Okay, so
Okay, he asked, do we need to change this discretization scheme for each
term,
iteration or
each term in the mass conservation equation and
I
momentum
don't think
conservation
so,
equation?
because everything, I mean, the equation there is described for any phase, because the principle of the finite or volume of fluid principle is actually you have an element. This element can contain up to 100 phase if you want, but describe only use single equation set that describe for what happened. But you will have another phase equation, which is alpha equal to alpha 1 plus alpha 2, which is alpha 1 is the gases or metallic and plus gas, and then you use that to describe, and then the equation is for alpha. It will split to alpha 1, alpha 2, alpha 3, alpha 4, whatsoever. It's number of phases you're looking at, but you use single equation to describe. Is that correct?
Yes.
Yeah, this is this called volume of fluid. But there is another technique that we may consider the phase separately. Again, you use a different equation to explain. I can't remember exactly how it's called, but that is another numerical technique you use. So okay, A is A, B and this is B, something like that. But I think that is probably the case for us. So we use a single set of equation to express the behavior of each phase.
Okay, thank you. Thank you.
Thank you. But this is traditional as well. And then I think this probably a very first time, apart from you go to, or probably not, in the software training, when you decide to buy them, they will go to such a great detail. Otherwise, it will be very high level description of the model, especially some paper. I don't want to say much, but this is, I mean, reality. Let's say early paper in this area, published from our national lab from USA. They didn't actually say any equation about how they derive this, but just show the result. Okay, I'm doing this. Yeah. So it's not actually what we want. We want to make it as open as possible, but to some extent, not everything, because it's still, we need to publish something, right? So is that finished, Hong Kao, or you are going to wrap up, or what? Yeah.
And at the end of the lecture, I want to share my experience to use the ANSYS front.
Yes, please.
Especially on about the UDF function, I think.
Okay.
Yeah. Usually I will use the this manual.
Okay. Yeah.
Yeah,
so
to find yes, this is manual to find which micro we want to use and what's the description or the usage and where to load or link the micro. Yes, for example, if we want to define the property of different material, and we can find
information here.
Right? Yeah, we can find this micro, and they will provide the description of this micro, and also they will say we can define the density viscosity and thermal conductivity, and after that, they will provide the usage, and there are three arguments we want to define or we want to provide, and here is the name of the properties, such as, for example, yes, I will define the density of alloy based on my simulation case, and also these two arguments will be provided or will be transferred from the ANSYS front to this code. So we didn't redefine this argument, and also I think the most important thing is that they will provide the example to tell us how to use this macro. For example, in this example, it's about a temperature-dependent viscosity property, and which means viscosity is varied by the temperature, and then they will provide the full code in here, and we can copy this code to our own file and make some modify or revise, and we can use this code successfully.
Sure.
Yes, yes, they will provide several examples, and also they will tell us where to hook the UDF. And for example, they will tell us the property will be used in this dialog box.
Yes.
Yes, and
yeah, thank you very much for this one. I think we probably have a few minutes left here. Can you actually present the last slide? So I appreciate that this is actually something we can. It's come with times, the skill and experience on this. If you are a PhD student or researcher, I think it's not just happen in one day or 1 month. It's actually the experience that you build over time, and hope appreciate that. So having said that, Hong Kao, can you summarize what we learned for today? Yeah.
Okay, thank you. Today I prepare a brief presentation about our research, mostly focused on the solidification from casting to additive manufacturing, and we learn the evolutionary mechanism of microsegregation for large-scale ingots. Also, we learn the effect of magnetic field on the dendritic grains growth. And furthermore, the multiple is predicted in our additive manufacturing process. Finally, I think our model can be used to predict the precipitation and something like crystal plasticity, and so on. Also, the external field can be derived from magnetic or electric field, and so on. And thank you very much for the listening, and that.
Thank you very much.
Okay.
Thank you. So very good. So thank you, Hong Kao. I think we will finish here, and then we'll catch up with you later. Thank you.
Okay.
Thank you very much.
Yeah, thank you very much. So I appreciate that. Yeah, so it's like case studies which we understood a lot from your PhD student. Thank you very much for that. And now, so yeah, the bus is ready at outside. So we are moving to the local trip. Before that, we'll have a small refreshments. Yeah, we'll wait for 5 minutes for the refreshments will come. And once we take the refreshments, then we'll proceed for the local trip. And for tomorrow, anything you can announce? Okay. So I hope everybody has corrected your name on the against your the certificates. So then all the best for your examination who opted for the credits, right? Anything else you want to let me know? Anything? Okay, let me know. Do you have any questions in general or technical? Maybe 5 minutes we can spend. Please, Arun. You were not there yesterday? Yes. Yeah. Yeah, that we have rescheduled it. Rescheduled in the sense like we are not going to do that. He's asking some labs. Yeah. So we have 2 more sessions from you. Yes. Yeah, then I think we have 2 more lab sessions. That is tomorrow. Yeah. Anybody have some questions? Yeah, so tomorrow will be like first 2 sessions, 3 sessions will be here after lunch. So we are going to have at the lab, additive manufacturing lab, that is one is printing as well as post-processing. Both the lab sessions will be there at the additive manufacturing lab. Yeah, we are going to divide the 3 batches. Now itself we want to divide it. Serial number 1. 3 batches. So you know your number, serial number 1 to 20, you know the numbers, right? So you have a unique number. So serial number 1 to 20, we have 1 batch. 21 to 40, 41 to 60. 3 batches. We'll go in 3 batches. So, yeah. Okay, then we'll take a break and then we'll take a refreshments outside and immediately we'll move on to the, so we'll call for the day today. Okay, thank you.